Se conecta. ¿O ya está? Ya. Das hatte ich dir erzählt, dass er in Oregon war. Wieder mal mein Handy vergessen, weil ich wollte ein Bild machen mit dem Workshop und Luna.
Super gestern. Wir waren schön essen
Mhm.
beim Bäcker noch. Die ganze Zeit gequatscht.
Das ist schön. Dachte ich mal.
So ein netter Typ auch.
Ja, ja.
He did his undergraduate and his master's at the University Cayetano Heredia in Lima, Peru, in biochemistry. Then he did his PhD in Miami, Ohio, also in botany, I think, right? And his postdoc finally in Vancouver, where we all would like to go, in British Columbia. Finally, he got a Humboldt Fellowship and as a Humboldt Fellow to Freiburg, Germany, and stayed there. How long did you say?
5 years.
5 years. So it's a long Humboldt Fellowship. I guess he eventually got a position there. And I think afterwards you spent some time in Madrid too.
Another 5 years in Madrid, yeah.
Also 5 years, and eventually he returned to Peru, where he's now a professor at the Católica in Peru, in Lima, Peru, and also director of the Institute of Nature, Earth and Energy at the Católica. He's going to talk about, have a little bit of detail about the Católica. I think I just
Thank you.
hand over to you.
So thank you very much, and I'm very pleased to have the opportunity to. I think it's a bit loud, Harley. It's very, very loud. Okay, yeah, if that's better. Yeah, I'm grateful for the opportunity to do a slight presentation of work that mixes a bit, combines a bit of biology, ecology, biophysics, some biochemistry, although it's not shown here, and a lot about sensors and especially networking, both at the instrumental level and also at the people level. So just to start, since I'm quite grateful that the past few days I've watched some of the talks, so I'd just like to present briefly my university. It won't take a couple of minutes only. So it's located in Lima, Peru. It's the oldest private university in the country, founded in 1917. I guess by European standards, that's very, very young, so we just turned 100 years old. Has around 20,000 students, including undergrads and grads, and has a whole gamut of careers available, especially in the basic sciences, chemistry, physics, mathematics, no biology, engineering, law school, humanities, fine arts, no medicine. So it's been a joke, and I think Waltraud has been also a professor at some point in time at the Catholic University. The biologists are essentially the Palestinians of the university. We just don't have a home. We just are in different locations. So I'm a professor of biochemistry in the chemistry department. There are biologists in geography and engineering and physics. But we still make a community that's actually getting pretty active in that sense. Just for the fun of it, I just put QS rankings. They're not particularly, I think all the main universities are now trying to avoid them. But it sort of places us against two universities in the area, Bochum and Münster. So we're somewhere around there. Although that's based mainly, I would say, on student rankings rather than on production. So what we'll be talking about today has to do with a project, a very long-term project, let's say a dream that has been materializing over the past 6-7 years, which is the setting up of a network to study essentially the eco-hydrology and also and its responses to climate change. And I will explain the reason for this in a moment. Now, it's been a slowly developing idea where we've had the cooperation of multiple sides. So in the end, I'm just going to be mentioning our acknowledgements to all the people that have contributed to this. So let's start with some 5 slides on just basics on the Amazon and the reason behind the project, and then we can just check the more technical part of it. So the first thing is that the Amazon obviously is not an ecosystem, it's a biome really, but it's a not homogeneous one. So what we have is basically 2 main gradients that determine it, let's say that define it. The first one is what we'd say a gradient of precipitation that goes from the Caribbean, let's say, part of South America in the north, down all the way to the Cerrado, which there was a talk yesterday about the area. That's where it ends. And the second part, obviously, is through orogenic reasons. Now, we have the rise of the Andes eventually in South America, and what you have then is that through erosion and water transport, we do have then richer soils on the western Amazon, and poorer soils on the older soils of the eastern Amazon. So those 2 gradients basically set up the scenario for differences in responses to climatic factors in those, let's say, forests, and the way they may be able to respond to anthropogenic and also climate change. So just quickly on the climatology of South America, basically we'd have essentially 2 contributions. The northern Amazon is basically influenced on something that's not in that map, which is the intertropical convergence zone, which shifts from north to south and eventually determines that the northern Amazon essentially is an area that has almost no dry season. It just rains constantly. So it's the wettest part of the Amazon. On the other hand, the rest of the Amazon is actually affected by the trade winds that you see there on the upper right-hand side. The South Atlantic convergence zone, which is that circle on the right-hand side of the picture. And then we have a transport system, a low-level, what's called the low-level South American jet, which is the one that moves then the moisture, the atmospheric moisture from essentially north to south. What's happening is basically something like this. Oh, again, I should be using this. So what we have is, the pointer doesn't work, doesn't it? But what we have is, we have massive moisture transfer from the east that essentially you would say provides all the moisture for the Amazon, but then you have a collision with the Andes. This is a process that has been slowly developing over geological time as the Andes rose, and eventually the formation of the Amazon basin, which originally was sort of a sink here, then eventually started developing an exit towards the Atlantic Ocean. This has generated basically three basins within the South American continent: the Amazonian, the San Francisco, and also the Orinoco. Although the Orinoco again is more influenced again by northern climatic processes. So the interesting part is that for the Amazon, what you have is you have an efflux from the Amazon basin of around 200 to 250,000 cubic meters per second going into the Atlantic, and the atmospheric transport is relatively somewhat larger than that. But if we would be talking about, let's say, like a checking account with a minimum balance that you need. That is, you have an influx and have an efflux through the different systems, but on the other hand, you need a base amount that has to stay in that account, and it's that part that will define how the Amazonian forest will look. In past geological periods, the Amazon has gone from forest to grassland, savanna, and then gone back to forest. And that's exclusively defined by the amount of water that's retained here. So the main question for many people, and those that have studied that long-term, especially in the central Amazon in Brazil, there are very good studies on climatic modeling of what the impacts are of deforestation, of rising temperatures. But the problem is that we do have what would be called the geologically speaking, the pockets of biodiversity have stayed during those periods where we've been shifting from savanna to forest. And those areas were near the Andes. Modeling atmospheric transport around the Andes is quite complicated, and trying to study the responses of those forests to the changing environment is also not quite well known. So we have a large amount of information on the central Amazon. We have still evolving, let's say, information from a large number of groups that work on trying to ascertain what is happening on this edge of the Amazon and how it will behave in the next years. Now the main part, as I'm pointing out then, is therefore the hydrology of the system. It's water that will define eventually what that looks like. So you don't need to be a climate scientist, and I'm certainly not one. If you're standing in the area of the Manu National Park in southern Peru, where the Andes are very wide, you have a point where you can actually look down into the Amazon. This is at 4,000 meters, and basically what you have there is the Amazonian plain. And you can see essentially how water transport moves and how the clouds actually start moving south from that part. So in the end of what I've been mentioning is that those gradients are reflected then obviously in the precipitation gradient that I mentioned before, and also in something more important, the length of the dry season. So you have in this part of the Amazon, which is basically Ecuador, Colombia, part of Venezuela up there, that have almost no dry season. And then as soon as you start moving sort of east and south, you start getting an extension, a progressive extension of the dry season to the point where you can get areas where you get up to 7 months of dry season, like the Cerrado, which can get up to 8 months a year of dry, let's say, no rain. And obviously, this is a classic picture from an ecology textbook, so to say. The central part, that balance of water, will define whether we have rainforest or we have savanna. And it's this shift that has been shown. I mean, the South American continent, the Amazonia, is essentially a very good explanation of how over time you can go this way or that way depending on that minimum balance of water in the system. So, just to finish now the introductory part, so what we have is, we have two processes that are basically unknown what the impacts would be. First, there's a suspicion, therefore, that with climate change, you will get then changing circulation patterns over the Atlantic Ocean. The result of that is you may have less transport of moisture westward, that is the influx of water from the atmosphere into the Amazon, and that might result eventually in moisture deficits in the western Amazon. Less will be hitting the Andes, and therefore we might get less rain. The second part is more complicated and has to do with the El Nino and Southern Oscillation, and it says that, you know, the intensification and frequency of these events might result, every time we have an El Nino, there's a drought in the Amazon. We've been lucky over the past 3 or 4 years because we've had La Nina, which is the cooling actually of the Pacific Ocean, and rains have been normal on the Amazonian side. So this is the climate. This is, let's say, the chimneys in developed countries spewing CO2 in the atmosphere. But there's another problem that we mentioned also yesterday and the day before in some of the talks. That is, we do have an active social component into this. The lack of governance, the occupation of land. We have the deforestation, therefore, threatens that minimum balance present in the account in a way that it's even more important than these two climatic components. So, how do you go about studying that? There's a large number of techniques. Many of them have been mentioned in previous talks in this event. So we have what we normally call the biometric and allometric methods, where you essentially have to move a field, a troop, let's say, usually 20, 30 assistants that work in the forest. What you're doing is on-site, you're measuring basically soil respiration. You cut a trench through the soil and just observe essentially root growth and check that. You have ingrowth cores that are put in there, and you're actually measuring how many roots start coming out of the container. You also put mechanical dendrometers on the trees, and every month or so you go and measure how much the tree has actually grown to measure biomass accumulation. You measure photosynthesis and respiration using infrared gas analyzers, and you can measure photosynthesis at the leaves, for you either get something that lifts you up to the canopy, or you have people that actually climb, and I've seen that, up to the canopy with these equipment and measure that there. You can measure the respiration of the trunks, you can measure the respiration of the roots using soil chambers that you put in. You collect the litter that falls from the trees to see how much biomass is being shed actually from the trees and going into decomposition. So there's a large number of methods that are constantly used, and ecologists that do this work on what's called normal plots, where they just basically go and check standing trees and growth, and use allometric equations just to determine how much biomass is above ground. And there's a so-called intensive plots that are very expensive to run on grants, and that do all these things in campaign type systems. Obviously there's different ways to observe this also. Remote sensing has been mentioned in a couple of talks before. So we have a number of hyperspectral techniques. We have also solar-induced fluorescence. So these allow us to have an idea of what is the primary productivity of those ecosystems. And also there's on-site methods, which I wouldn't say are any cheaper than these here, but that have permanent infrastructure on sites. So these are the flux towers that use a system where they're measuring then exchange of trace gases and water vapor between the ecosystem and the atmosphere. And that's what we're going to mention in the next slide then. So basically what one is trying to look at in all these measurements that have been shown before is to determine the gross primary productivity and the net primary productivity of the system. Most of you may have some background in biology. Just basically know that gross primary productivity is the entrance basically of carbon into the ecosystem. But net primary productivity actually measures what's going specifically into biomass formation. So since biomass formation includes long-term biomass because it depends on cycling times, and you have, for example, a trunk that will last a very long time, and you have leaves that, depending on the species, may or may not last that much time, You have to measure the dynamics of the process, and that's why one checks on liter fall. And you're measuring also, since you measure carbon intake, you have to measure carbon going out, and that comes from all the respiratory processes. That is leaf respiration, stem respiration, soil respiration, CO2 that's produced through decomposition. So that's basically more or less the story, and obviously there's another component that at least one of you has mentioned before, which is the fact that plants are basically emitters of volatile organic components, and that's also a part of carbon that has to be taken into the equation. So now we get into the other part. How is it that we measure then exchange of trace gases and water vapor from the ecosystem to the atmosphere? For that, there's basically a theory that has been refined over the years, and of whom your predecessor, Thomas Focken, actually contributed quite a bit, which is eddy covariance. And what eddy covariance is measuring essentially is the net movement of mass from the atmosphere into the ecosystem, and from the ecosystem into the back into the atmosphere. And so we're checking in a movement where you have atmospheric transport that may be moving in any direction, and that in contact with the surface does develop turbulent transport like the ones you're saying, and you see all these eddies here. What this system is trying to do is then to try to measure at a certain instant in time the effective transport of a amount of mass from the atmosphere into the ecosystem, and from the ecosystem into the atmosphere. For this, okay, one uses, let's say, the basic eddy covariance equation, where you have essentially, you're measuring the average vertical flux, for example, of CO2 and water over a 30-minute period. That's being measured about by fluctuations or changes in the concentration of water or CO2 around the mean. And you have to know also the velocity of the air being moved upwards or downwards in the system. So this is basically the essence or the heart of most of the eddy covariance calculations. For this, then, you have a number of components that have to be used. And of course, to this you can start adding a lot of extras, like in a car that you're buying. But the central one is the high frequency component that's shown on the left-hand side, where you have a three-dimensional sonic anemometer that's working at a very high frequency, usually between 10 and 20 hertz. You also have a system that essentially is determining the concentration of an infrared analyzer that's measuring the concentration of CO2, water, or methane, or some other component that can be analyzed by that technique. And what you have, this one is an infrared analyzer for water and CO2. And this one's what's called a closed system, so it's actually actively sucking air at between 10 and 15 liters per minute, and is located close to the 3D anemometer. What we're having then is information on wind movement at a certain instant, and at that same time, this instrument is telling what is the concentration of CO2 or water at that moment. But eddy covariance not only depends on just mass transport along a 3D axis, but also you need information on energy, so that you can close a balance. You have both energy and mass into it. And for that you have sort of mid-frequency measurements that include the radiation that is falling into the forest, long and short wave, and the radiation that's being reflected or emitted from the forest into the atmosphere. For that you need that net radiometer. If you want to estimate a bit more information, you need photosynthetically active radiation, so you have a radiometer for that too. You can check temperature and relative humidity. And associated with that, you have all the climatology and associated side measurements that provide more information into what you're observing here. So one of the things that we're going to see in the next pictures is CO2 concentration is not only just say CO2 is just not slightly moving up. Depending on the atmosphere and wind transport, in closed canopy forests, you can get, for example, CO2 accumulation. So what you need then is a system that senses CO2 concentration from the canopy down to the soil, and for that you use a CO2 profiler. You also need probes in the soil that will let you know what is the humidity in the soil, will give you an idea of how much water there is for evaporation available. You can have also all kinds of sensors associated to the trees, and Jan Sontag will mention after this talk some of the systems where we can actually try to measure by proxy what is the transpiration of trees into the atmosphere by using digital dendrometers. And of course, in systems like these, we have precipitation, and therefore we use rain gauge. It's amazing because we had a system in the Peruvian desert. Obviously, the rain gauge was not part of the system that we needed because it never rains there. On the other hand, we did need to find out how much water condenses from the atmosphere at a certain point of time, and so we had a system to measure that accompanied it. So there's usually one can get basically fairly clear information on what's happening, this depending on the types of sensors that we have that are associated with the tower. And usually that might imply putting a lot of cabling around. But on the other hand, you can also use wireless networks like LoRa networks that some of you have been mentioning in the past few days to actually communicate with the tower system. So what's the idea? The eddy covariance towers were set up a long time as part of the called LBA project in Brazil, and they have been located and running for a very long time in the central Amazon, the Brazilian Amazon. Basically, Brazil was the testing point for most of eddy covariance in South America. Now, there's currently the largest tower in the American continent is the Atto Tower that's run with Max Planck Institute and INPE, I think, in Brazil, which is a 300-meter tower going into the sky near Manaus, where they measure not only then ecosystem effects at that level, but they're measuring essentially atmospheric chemistry. So this was the situation. This is run through the Ameriflux network. The Ameriflux network is a network of eddy covariance sites that are located in the American continent, and these are the registered ones as to, let's say, a couple of years back. These are all fairly new, so they come from only 4 or 5 years back, but this has been running for at least 15, 20 years, I think. I'm not exactly. Do you know how long the first covariance tower in Brazil was? I think it was.
It must have been early 2000s.
So it's 20 years. 20 years, yeah. Okay. So the idea is that we're working on a network called the AndesFlux network, which initially is starting in Peru because we're just sitting next to the Andes, and the sites that we're sort of have, and some of those that are in plan, are the ones that are running are the two in the south, the Los Amigos and Tambopata. This is an area that's getting into the drier part of the Amazon. We have finished now one in the central northern Peru, which is an area that has quite a bit of precipitation. And there's two planned, one in Ampillacu, which is run not by PUCP, but will be run actually by the Peruvian University of the Amazon, and in Panuana, which we're hoping to finish on an agreement with the foundation there to set up a tower. So basically we have essentially, let's say, half the network already installed. And as will be shown on the next slide, the interesting part is these towers are very close to the Andes. Essentially on a clear day you can see the Andes from them. These are the Los Amigos and the Tambopata towers, and they're both about 100 kilometers from the Andes. The important part is they're that close to what would be the widest part of the Andes at the time. Why is this important? Because this part of the Andes actually have a very definite and strong influence over climate in this area. The reason is that if you have a plateau at around 4,500 meters altitude, it gets a lot of energy from the sun. It heats up. So for example, one thing is that well known is that part of the Peruvian and the Bolivian altiplano generate what's called usually the Bolivian high. The Bolivian is a high pressure system that actually influences the south-going transport from the South American low-level jet that will transport humidity all the way to Argentina, to the Cerrado. So it has an important effect, and it can determine how much water is being moved south. Now, just to mention this briefly in Tambopata, this is a windrose, and what we're seeing is during the wet season, when you have the South American low-level jet working, you're getting then this stream of moisture from the northwest, which is just bordering the Andes. So that interaction with the Andes is the one that's meandering and causing, making difficult to model. On the dry season, that changes completely. So you have about 5 months dry season in the Tambopata area in southern Peru, and you can see that moisture transport, atmospheric moisture transport changes direction completely. Now it's coming more from the Andes themselves, so you get some cold fronts going in, and you can get some wind also from the southeast. And usually the profiles that one measures in the tower would be these. This would be essentially the combination of water flux into the atmosphere coming from evapotranspirative processes, that is transpiration from trees and evaporation from the soil and from the canopies. And this would be a CO2 profile. You can see here that this would mean zero means zero net movement. If it's up, means it's going into the atmosphere. If it's going down, then it's moving into the forest. So in the case of CO2, when we have this part here, it means that we're incorporating CO2 into the vegetation. And when you have this peak out here, then is when you are getting actually CO2 from respirative processes moving into the atmosphere. And this is what I was mentioning before, why we need profilers, because what you have here is then that early in the morning, around between 6 and 7 in the morning, you can see when wind starts moving, when the boundary layer, let's say, rises and you start getting movement, then is when all the CO2 that has been stored inside, like if there were a cap on top of the canopy, starts moving up, and then you get this pulse of CO2 into the atmosphere. So that's a wet season, dry season. And of course, this, I'm not going to go into much detail. I'm just not quite short in time. But the other thing one has to do is to check precisely the energy balance. So what you have is you check sensitive and latent heat, which are basically the energy needed to heat up, let's say in this case, if we're looking at water, and the energy that's needed also to have a change of phase in the water. And you check it against total impinging radiation. And usually when you set up a plot like this, the slope will tell you a bit about the closure of the system, how much of that information of energy you actually have. This one was done, for example, without sensors, heat flux plates, that is, those that actually check the amount of energy reaching the surface of the soil in the system. So we have a closure of about 66%. We still have to get another 34% by working a bit harder with sensors. And these are just, the other problem with towers is that they don't register constantly. You always have problems, they stop. And you have to send somebody to fix them. So when you have a plot like that, usually there are a number of programs available that allow you to do what's called gap filling, which is not cheating, but essentially it analyzes, and in a previous talk, somebody has mentioned about that a bit. You measure essentially the profiles of how it's been going and how it continues. And with that information, you try to fill the gaps in the profile. That's just respiration, gross primary productivity, and what's called net ecosystem exchange. You can see that gross primary productivity is always a positive value, except when you're actually losing biomass. On the other hand, net ecosystem exchange is measuring what goes up and what goes down, so it's centered around zero, like we saw in the fluxes in the previous images. So the story of all this is after you collect all that, you end up having something like this. So we have, and this explanation is not purely an explanation that comes from just the physical measurements being done, but it has to do a lot with the ecologists working on the ground. So what we did here and we presented this here at the American Geophysical Union meeting in Chicago, is a combination of using eddy covariance profiles together with satellite information, together with on-site information. Combine that all, asked a modeler also to work on that, and the result of this was that we have increasing mortality of trees in the southwestern Amazon, and that's resulting in the so-called shift from being a net sink for CO2 into being a net source of CO2. That is, the forest is already starting to throw out its extra CO2 into the atmosphere. And that's critical. But the explanation comes really from one part. The mortality, and that's an observation of the ecologists, was shown because there's a group in Leeds that actually made the first hypothesis, and this has only confirmed that, is that increasing CO2 concentrations make it possible for species that actually can use CO2 quickly to actually increase in biomass. And those are not the big trees that actually keep the forest together. Those are the lianas that just hang on the trees, the parasites, let's say. And those actually develop profusely, and what they do is they add a lot of weight to the trees, and when you have some extreme event like wind, a storm, at that moment the bigger trees start falling down. So this is what's happening in the Tambopata area, and when one walks there, one can see that. You have these huge gaps at times in the forest, and you can see when you go into the older part of the forest, just the huge liana populations. So this is showing us a bit how the cooperation between groups doing all the techniques actually can provide a story behind the event. And now, just to close, because I think Jan will explain this a bit more once after my talk, is that one of the things that we've been trying to put on is the Andes Flux Network is not just a bunch of towers set in the forest. They all have plots set around them, which have sensors and which are constantly being measured. And one of the things that we wanted to definitely start using is to try to measure evapotranspiration from those trees. The forest is not made of just one species. It's not the Black Forest where you have just one single species or a couple there. We can have up to 100 at times different species in the forest. And each one of those species uses water in a different way. They all have different, let's say, bank account types. And the only way to start looking at that is to try to measure how much the tree transpires. And we did this experiment, and this is obviously not the jungle, this is the Peruvian desert, and it's an olive grove where we actually worked on this. And sorry about that, this has a lot of information, but it just, this is the flux of water from an olive grove. So you can see daily flux averaged over several months in the growing season. You can see that the main efflux of water into the atmosphere from evapotranspiration comes around noon. You have around 11 in the morning to around, let's say, 4 o'clock in the afternoon, you get the maximum amount of water flowing into the atmosphere from the trees. Here you have just soil water content. And here what you see is the stem diameter fluctuation of the trees. And one thing you could say is, okay, you have biggest efflux of water into the atmosphere, and then you would have the minimum diameter of the tree. Because as the tree is just losing water, then the stem shrinks. But you can see that in the case of olives, it's shifted by about several hours. You know, peaks are around this area, and this starts around, let's say, 3 o'clock in the afternoon and goes a bit further while you have the bottom part. And that's showing that, if you realize here, early in the morning, you have the maximum diameter, so you have maximum water content in the tree, while efflux of water is going into the atmosphere, but it only around sort of 10 in the morning starts shrinking, so it starts showing. We have a storage component in the tree, and the olive is well adapted to arid environments and tends to do that. There's work also by Spanish groups in Andalusia, which show this very clearly, this storage component by olive trees. So this is telling us information that we would like to actually add into this whole eco-hydrological story. That is, each one of those sites will be equipped with these type of sensors, along with soil moisture profilers and all. And I think I exceeded my time. Thank you very much. There's been a lot of people involved in this, and I can just barely start thanking a number of them, and also a number of financing institutions. Amazingly enough, Peru also gave quite a bit of money, close to $1 million for most of the project. Thank you very much.
You mentioned in your introductory talk that the South American convergence zone may weaken, and hence the influx of moisture into the upper South American continent may be reduced with projections. What's the reasoning then? Do you know anything about this?
No, that's yeah, I understand that. Yeah,
I mean, that's the actual motor that
yeah. For me, I mean, okay, for a lay person like me in the area of climatology, I always thought higher temperatures, increasing temperatures, also ocean temperatures, you get more evaporation. And I would say, naturally, you have then more movement if atmospheric transport remains the same. But the question is now, does atmospheric transport remain the same? And according to climatological models, apparently it may not remain the same. You're already having alterations in the intertropical convergence zone. And some of them are normal. You've observed, I mean, we know those periods when actually the interconvergence zone doesn't move that much, and you're still getting droughts south of the southern part of the equator. I don't know what the climatological model that results in this. The information comes basically from papers and from Jörg Bendig's group in Marburg, who's speculating also on that, because they have this study on atmospheric exchange between the western and the eastern fronts in South America around central Ecuador, which is the part where the Andes just kind of are lower, and you get some leakage of atmospheric moisture transport from both sides. But more,
expect the opposite. Like,
yeah, me too.
it warms up more, you know, it actually fuels the convergence.
But it's the old thing you say, okay, you get more people in a city, you get more people, you get more people at the bus stop, but you need the bus to move all the people. And the bus problem is the atmospheric transport. Don't know. Well, once again, thank you. Oh, Ute. Oh. Can you repeat that part? Sorry. Mhm. It depends on the plant. Again, the plants have managed their water in certain ways. So trees or plants, let's say, that the moment they start losing the water reserve they have, close the stomata, and then you see the depression. Other plants that have a buffer, let's say, in them, like in this case the olive. In the olive, you don't see that. I mean, evapotranspiration just goes like a peak and then goes down afterwards when the temperature goes down. So that is actually what we would like to see, for example, in the forest in the Amazon. See which species actually are more affected. That's something that Yadvinder Mali also says, that it will depend on some types of trees that are actually more affected by drought because of the fact that they don't have the water management, let's say, incorporated into their physiology. So right now we just have olives, unfortunately. Okay, the project originally had foreseen using LoRa for the measurements, And we do have some, but there were problems during that particular. So the data that you see there were not done with LoRa, they were done with cabling. Mhm. And that's why I'm hoping that Rolf and Jan may be able to help us a bit with the system, yeah. No, that's a closed, the one shown there was a closed path one. So there is, you have a pump. Okay, the problem with, one tends to use closed path instruments where you have a lot of precipitation, because that interferes. When you have an open path system is an infrared analyzer where you have essentially the laser and the detector open to the air, so air is just essentially moving through this arrangement. And a closed path system is one where you have a pump essentially that's sucking air into a cell that's analyzing that. So usually, as you may have seen there, the cells have a cup. So one of the problems that we've had is normally we extend the cup by a centimeter or two, although that has some problems because of the fact that we do got a lot of horizontal rain and wind in the Amazon, and the system starts sucking up water. So the main problem is that. So we have also an open path system that we've used in the olive grove where it doesn't rain. Oh, no. Pardon? All the VOC studies have been done in Brazil. We've only done measurements of VOC concentrations using cartridges, and can see usually the peak in concentration around early noon and then goes down. But it's for us super expensive because we need to essentially collect that in cartridges. We were talking about that a bit yesterday. We're using Carbotrap also. We were using mixed, and those cartridges are shipped back to Lima, and you have to put them in a thermal desorption system and run on the GC. So it's quite a lot of work. So we decided for now to just give up on that.
I've never seen balances of VOC actually part of the carbon cycle. I mean, studies, intense field studies, absolutely, but I've never seen a contribution, the carbon cycle VOC transfer is like that percentage. I've never seen it.
I've seen a lot of speculation, huh?
It can, absolutely, no, but I'm saying like, typically these studies are so labor intense that you tend to not have that.
Well, the ones that they have done them.
Okay. Annually, over like long-term observations, do you see flux, not concentrations, flux?
But they've done campaigns. The people at Max Planck in Mainz have done PTR MS, where they just bring the whole mass spectrometer to a tower and they can measure things, directly. Yeah, but that's super expensive. You can't put a PTR mass spectrometer in a tower constantly. Oh yeah, well, if you have a few $1 million, yeah. Yeah. No, but I have no idea. I've just heard that values around 10% or something like that in some cases, but that looks exaggerated. But yeah, it's I think Josep Peñuelas from Catalonia, from Barcelona, is the one that has been working quite a bit on that too. But that's mainly on Mediterranean systems. And it was Kesselmeyer, no? Jürgen Kesselmeyer, that just retired, that had been doing that in the Amazon. Well, thank you very much once again.
to go into measurements to lower one. And I'm going to tell you a little bit about Jan. He is a graduate in media communication and computer science of our university. He works on front-end, back-end, and embedded development systems and is involved in a whole number of projects together with Rolf in the EO lab. And for example, we heard a talk about the Crunchy Cloud project, and now Jan is going to tell us his contribution and the contribution of Rolf towards the Andes Flux project.
How does this one work? Okay. So, hello. As you may can see, today I want to talk about the usage of LoRaWAN and sensors in the Andesflux project. You already heard a bit about which sensors we want to use, and we are still in the testing phase of what we can do. But also I want to explain a bit of what is LoRaWAN in general, because we heard it I think 1 or 2 times already during the conference, but probably some of you may have no idea what it is. So I want to give an insight of what LoRaWAN is, how we want to use it, and why we decided to use it at all. But first, you may already seen the tower in the previous presentation. This is the tower in Tambopata. And this is just to give an insight on what we are working with. So we have this tower, it's around 40 to 50 meters high, Eric, yeah? And you see it's the top of the tower is over the canopy, and it's located here in Peru. We already saw that as well, but let's go a bit closer because we just saw a big map. So we see it's somewhat remote location. This is around, I measured it yesterday, 28 kilometers away from the next town, Puerto Maldonado. So we have maybe a connectivity problem in this area, so we somehow need to get sensor data from there to somewhere else. And you see there's basically nothing around it except some, I think these are some fields, there's like something, and here's a small lodge where we where Eric used to go. But now let's go, what do we want to do exactly in the Andesflux project at the towers themselves? So we have a tower, we have some, or 1 tree in this example, and what we have 2 different kinds of sensors. So we have ground level sensors that measure something at the trees or in the ground, or maybe the air around here, close to the ground. And then the other thing we have is the sensors that are on the tower that Eric just explained. So the for example, the smart flux system which sits on top of the tower, where also all the power is generated through solar cells, for example, because as you saw, it's a remote location. We don't have like an AC outlet where we can pull power off. And what sensors do we sensor, as you may can see, and there's a wire going around a stem, there's a small pull or push rod that's going in and out, and you just measure resistance. That's the whole principle of the dendrometer. But also maybe in the future we want to have more sensors. This is a sensor we worked with in another project called Internet of Agriculture. You see it's fairly heavy as well. It's completely filled, so it's a very rigid sensor. And it can measure soil moisture in multiple levels. So you not only have one value at the top maybe, but you have like 3 different sensors, and you can change even the distance. So you can manufacture them so that you, for example, have 4 or 5 levels of soil moisture measurements with one sensor in one tube. So this is what we want to do. But now we have some requirements that we want to meet. So, for example, we have cost. Okay, it's very costly to install something there. Someone has to go there. Maybe you have to lay some cables. So we want to keep with all our sensors that we want to deploy the cost relatively low. Also, we want to have it low on maintenance, so it doesn't help if I need to go there every 2 weeks, every month to change out a battery or to read out an SD card to get to a USB stick. That doesn't help us in the project because, as you saw, it's a remote location. We cannot just go there immediately. But also we want a high flexibility, so the system needs to be adaptable. We need to have all sorts of sensors compatible with the system. Maybe we need to make some bridges between the sensors, but we need to have the possibility to use them at all. So, what can we do to like connect all the sensors? Okay, at the top of the tower, maybe we can have some cables running. But if we want to go down into the forest and we have like a couple of sensors there, lay a cable for each sensor isn't an option. It's a very high cost, and also the cables might get broken. So basically these are the major wireless connectivity standards there are. We have some that are meant for a local area network, which include Zigbee, Bluetooth or Wi-Fi, maybe you heard of them. Then we have cellular, which is normally LTE, or you heard of NB-IoT, which is a bit more power efficient. And then we have LoRaWAN, which is a low power wide area network. You see there are some pros and cons to all of them, but basically you see cellular is licensed, so most of the time you have a monthly or yearly fee you have to pay. There in the forest, there is no coverage of LTE, at least under the trees. So basically this option is not going to work for all our ground level sensors. Then we have LAN, okay, we could use Wi-Fi or something like Bluetooth or Zigbee, which normally work on the 2.4 gigahertz or 5 gigahertz range. But to be honest, as you might already see, they have a very low range, and the tower is already 40 meters high. Okay, maybe we can get like a bit of Wi-Fi around the towers, but if you want to go deeper into the forest, this will also not really be an option. But it has an advantage. It has a very high throughput rate, so we could stream a video or something or photos over it. And then we have LoRaWAN. As you can see, it's unlicensed, but it has a very low bit rate. But if you think about it, like the sensors, dendrometer, or even the soil moisture sensors, it's basically one value that we need to send, maybe also a battery value. It's a very small amount of data, so this isn't even a problem for us. And LoRaWAN normally works over the unlicensed spectrum in the 886 megahertz, or in other parts of the world 915 megahertz frequency. It's unlicensed, and we can build our own infrastructure at the tower. This is a great advantage because we can just deploy our own infrastructure, and so that there is coverage at least around the towers. Also, LoRaWAN enables us to have a very long battery life on our sensors, so you don't have to go out like every month to change the battery. We can even get sensors running on one battery for multiple years, up to 10 or even 15 years. And all of this is rather low cost to set up, and also there are a lot of sensors already on the market that you can buy. There are already soil moisture sensors that you can just take and install, and they will be compatible with the LoRaWAN standard. I will go into a bit more detail what else is great about LoRa, because that's part of the presentation. But now maybe we go into what is LoRa. So you heard it a lot, but what is actually behind the whole LoRa standard? So as I already told you, LoRaWAN is a low power wide area network wireless communication standard. And because it's a standard, everything is basically defined. And this is all done by the LoRa Alliance. Since a couple of months, our university is part of the LoRa Alliance. That's why you see now all the logos and the LoRaWAN logo here. And also they did some of the nice graphics, which helps. But in principle, what is happening? So we have a device, and this device is LoRa capable. Supports LoRa, for example, and LoRa stands for long range, and this is really just a wireless modulation standard, so it's just the physical layer. So LoRa and LoRaWAN aren't the same thing. LoRaWAN describes everything, the whole system from device to the application in the end, to your dashboards, for example. So what happens first? The device talks LoRa, so just the communication, to a gateway. You can imagine the gateway is something like your router that you have in your home. So all the devices communicate over LoRa, and there are some predefined like protocols. It's the LoRaWAN link layer, for example. So they talk over this, and then the gateway receives some data, and then you see here there's just a gray line and doesn't say what is this. And this is an advantage. We are not limited to one communication standard after the gateway. We just need to connect it somehow, it doesn't matter how, to a network server, and this network server manages all the devices. So you want some security in this, and this is why LoRaWAN is built so it has bidirectional security from the device to the end, the application server, and back to the device itself. You can also send data in a bidirectional manner. And the network server manages all the devices, looks for the authentication for some magic to the application server, where you can already see you can make some nice graphs and do more with the data. So send it to another application, for example. But this is the whole structure that is LoRaWAN. Yeah. And now you can see this Donna Moore is the CEO of the LoRa Alliance, and she says there's no single communication technology that can support all IoT use cases. You will not use LoRaWAN just with LoRaWAN, because there needs to be a way to get the data out of the system, from the device to somewhere else. So normally you use it with other technologies like 5G, because the gateway needs to be connected to, for example, another server or a computer, the network server and application server. But also LoRaWAN can work in conjunction with Bluetooth or other technologies like Wi-Fi or RFID. The idea is, if you, it says it here, protect legacy tech investments. You already maybe have some sensors, maybe they are Bluetooth, for example. The idea is you could build a bridge from Bluetooth to LoRaWAN, maybe like a small concentrator Bluetooth board that connects to your Bluetooth sensors, and then this sensor board or this concentrator board sends out all the gathered values from Bluetooth and sends them over LoRaWAN to your cloud. So you can even connect other older or legacy sensors that you might still want to use, but have them in a remote location. Now we're going to talk a bit more about the practice, what we are planning to do in the AndesFlux project. So you already saw how LoRaWAN works. So what we have here, okay, we want to communicate our sensors over LoRa. They talk to our gateway, and then there's some IP-based communication, like your normal Ethernet and your normal Wi-Fi. So the gateway can talk to a network server and the application server, and then there is more IP-based communication to your dashboard, your application, your database, or whatever. Sounds good, sounds easy. Problem, you remember, we are on the edge, we are in the forest. So what we normally do when we are here, when I use my sensors outside in the GFL or in other projects, we have our sensors, then there is a gateway and a router somehow connected over Ethernet, and we use a cloud network and application server, because why should we get into the hassle of setting everything up? Might be a router, because we have other sensors that we want to connect as well, and it has just a mobile connection to the outside world, because if you are on top of the whole canopy, there is actually 4G connection, so we can use 4G to connect the whole tower as itself. There's just no 4G connection down in the forest. But what happens if the mobile connection now breaks down? All our data gathered over LoRa would now be lost, because there's no connection to the network and application server of LoRaWAN. Would be a problem, because we want the most data that we can gather without any gaps in the measurements. So the idea could be we use LoRa, the gateway stays the same, but who says that we need to rely on the cloud provider? The network server and application server can also be hosted yourself. There are open source variants that you can use. So there's documentation out there on how to do this. And then the database could also be local at the tower. So there's a local database that's always up to date, no matter if the connection to the internet breaks down or not. So no data is lost in this scenario. Okay, if the power goes down, then we have other problems, but in any case, if there's power, we have the data. But then we somehow need to access the data. So the idea is we have our local database, which is over Ethernet connected to our router, and it has a mobile connection to a remote database. And then through some database magic, we can sync both the local database and the remote databases automatically. So the local database will always be up to date, and whenever there is a mobile connection, the remote database gets updated and we can access all the gathered data basically live, as long as there's a mobile connection. Otherwise, we have the most up-to-date data. This is the whole idea what we could do. And then to expand the system, LoRaWAN, we could easily do this, but we already have a local database, so we already or also can attach the eddy covariant system that Eric explained earlier, connect them to the same router and also save to a local database. And whenever there's a mobile connection, we can sync even that data. So the system is expandable. Let's see. Right. Now we can get back to this. As I said, no single communication technology can support all IoT use cases. There are other options to solve this problem. What could also be done is, if we want to rely on the cloud service provider, we could also use a satellite connection like Starlink and have a failover. So, if this mobile connection fails, we could also jump over to another technology. We could also say, okay, if mobile fails, let's go through satellite or the other way around. Then we wouldn't need the local database, but still, this would probably be the most reliable solution, because if both break down, both solutions, then data would be lost. But yeah, still, you have to think about LoRaWAN can do a lot of things, but you need other solutions as well. I want to talk a bit more about the current status of the project. As you may can see, I went there last year. It was a bit warm, but yeah. And they didn't have water, that's why I'm drinking Coke. Only reason for that. What I wanted to show here on this picture, you can see what they are using right now, what they tried out. So this is a very big battery, and was like this big, very heavy. And then they used a almost 2,000 euro data logger from Campbell. They couldn't get any data because it didn't have a remote connection. It was saving to the internal storage. That was it. I got this thing back to Lima, so it lasted 5 days, and we couldn't really get any data out of it. And I installed the first prototype of a dendrometer LoRaWAN sender node. It also held for 5 days, but it didn't cost 2,000 euros, so that's a plus, I would say. But we did our first test with LoRa in the forest. It was working for 5 days basically, but I think I saw it was a software issue, not a connectivity. Smart flux system, for example. So the Lycor LI7200 is connected. That's the one that Eric uses there. We did some first LoRaWAN test, as you already saw. We did some first dendrometer prototypes, at least the sender node. We buy the dendrometers from a German company. And we did a proof of concept on the automatic file syncing. So, for example, the data from the Lycor system already can be accessed from a server here in Germany. Unfortunately, we need to up the mobile data volume a bit, because it's quite a lot of data and I cannot download it right now. So we need around 40 gigabytes per month to really have the automatic file sync working all the time. You see here, we can later have a look at this. This is the dendrometer we installed back there in the Green Fab Lab. This is currently the sender. I attached a longer antenna to first check if the hardware is really working and get rid of the communication problem. It's a bit of a bigger antenna. It's not internal right now. But right now, with the bigger antenna, it's actually working pretty well. So I will try it hopefully out later this year in the Amazon rainforest. We also installed Node-RED to gather the data, play with the data, and have the automatic file syncing done through Node-RED. Maybe I can show this later in the workshop how it's done. And an OpenVPN is set up so I can connect to the tower, as I said already. Any questions? Yeah. Low power means really low power consumption. So with our sensors, we normally go. Okay, you have to differentiate a bit. There's low power consumption in the sleep state because you will with LoRaWAN you only send like every 20 minutes, for example. You will not send all the time because this is also a regulation of the unlicensed band from the government, basically. So you send, for example, every 20 minutes, and in the meantime you sleep. The controller just sleeps and does basically nothing. It just needs to keep active. Okay, I need to wake up in 20 minutes. That's the only thing it has to remember. During this time we use about 10 to 20 microamps, so very low. And then during sending, it gets up to, normally if you average it out over a 10-second period where you measure and send the data, you measure around 2 to 3 milliamps in average over the whole time, yeah. But the peaks go up to 120 milliamps during sending. Yeah? Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Yeah. I measured like for a week now, and the data is there's not really that much happening. So it stays flat, flat, flat. Only when it freezes, it does something. But yeah. Thanks. Yeah.
Yeah, thank you for spelling out all the fascinating options of combining networks.
Mhm.
Just a quick question: the SmartFlux system that you currently have connected is not connected by LoRaWAN.
No, no, no. It's that's connected through Ethernet because it's on top of the tower directly to the
In addition
router.
to, are you actually pulling the raw 20 hertz data? Are you synchronizing, or do you use
Um,
the SmartFlux output? This would be one question. And
yeah.
could you imagine, let's say you have often we use sub-canopy eddy coherent systems
Hmm.
for look basically at the flux closer to the ground.
Hmm.
And if we were to send some statistics through LoRaWAN, so not
Hmm.
the actual 20 hertz data, but
Oh yeah, the computer data, right? Yeah.
processed fluxes, is this something? I mean, I
Hmm.
try to do the math: 50 kilobits per second
Yeah.
maximum transmission rate over which distances? Do you have
Um,
some
so in the forest, it's a bit harder, as you can imagine, because there's a lot of stuff around, a lot of water stuff. There are ways to accommodate for that, so you can go deeper into the forest, but let's say we stay close, like 500 meters to the towers. Um, so could be hard. I would have to check how big the data actually is. So I think with one payload you could send really not that much. It's a 256 bytes is the maximum per send. So you probably would have to split the data. Yeah, but I would have to look into like the exact. Maybe you could split, but it would just take some time.
back to the first question? Do you actually
Yeah.
synchronize the 20 hertz data
Um,
top of tau, or do you get
The raw, the raw. So right now I'm synchronizing raw data. So the idea is in the end to have everything that it measures, just everything. So raw and the already computed ones, but I just started with them. I just got into the file browser and saw, oh yeah, raw data looks good. That probably you can do the most with the raw data, I thought. But yeah, the idea is to have everything in the end. You? Yeah. Yeah, yeah. But that is then not my task. Eric can do that stuff. Yeah. And so my task, I know how to access the data, how to get the data, and I can also visualize it in the program of Lycor. And I'm sitting there, yeah, looks like data. And then Eric can do the rest and his team. Yeah. hopefully. Yeah. 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 And then there's already new data. Isn't that great?
Let me ask Christoph Thomas. He's a guest on short notice to our university. He's an expert in all kind of flux measurements, micrometrology. His background is geochemistry. He's professor at the University of Bayreuth. And I think he's a renowned specialist in the evaluation of eddy flux measurements, right? How do you
Yeah.
do it? How many methods do you exploit?
Well,
Want to join the podium here?
no, I can't. I mean, I'm certainly, I could, if you give me 5 more minutes,
Yeah, 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 sure.
I could present a couple of slides if you wanted to.
I think it would be a good time now, really, to continue with maybe your research, right? To give us a short insight. That's okay for you, right? Also, no.
Or we allow him to prepare while Antonio is talking.
I think that's an excellent idea. I do have my computer there. I could put together something to look at.
But just a
Just
quick
to
question:
look.
how do you do this, right? So you're gathering data, and because you're also working in the Arctic, also Antarctic.
Antarctica as well.
Oh wow.
I mean, actually processing the fluxes, it's not that difficult actually. We have written our own programs where this is kind of our business we do. And the actual statistics is not the difficult, it's then the interpretation and the fine tuning to that actual system. But it can be done, I think, I think that's the beauty of it, by combining forces, joining forces, having,
Mhm.
experts on communication technology, ecophysiologists, and then the micromet people who do the flux analysis. I think this is, you can only pull off these larger projects when you combine forces, join forces. But it's, the actual math is, there's available tools, even Lycor offers the smart flux package.
Yeah.
Which I'm not a huge big fan of, but still, they offer it, it's doable, but the flux business is a little tricky.
And there is even a summer school, which is now rather a spring school, which you are offering to learn all the evaluation and the analysis of the data, right?
Yeah, I mean, I could also pull up a slide or two on the presentation that I may give on the fly. So we do offer these classes. So if any of your students is interested in learning this, eddy covariance technique, we offer a summer school, spring school, 14 days, one-stop shopping with lectures, setting up instruments, processing, report writing, evaluation, so you can learn how to do this. This is what we've been doing for many, many years. And my predecessor, Thomas Foucault, he was one of the, as Eric mentioned, one of the kind of the grandfathers of this flux community who made this technology or made it available to others, to other groups who are typically not micromet experts, but they just want to use the fluxes and the tools. So we train people, but it still takes a lot of expertise and finessing. But it's doable. It's a doable job.
Yes, of course. I'm the old times. Now you're better.
Yeah.
For the moment, we have a quick list, but then return later on to the flux, which is basically the basic theme of the day. But so that you can all relax your minds, we now go into astrophysics, right? Anyway, Kenny Antonio Lectare will present, and which will give Christoph a bit of time to prepare for his small little on-the-fly talk.
Okay, sorry about the delay. So I am just going to give you sort of a touristic scientific booklet about what your students here at this university and around the network can do in Tenerife. My idea is to show some of the ideas and to show Tenerife as a laboratory. So your students can go for a final degree project, master projects, and this kind of interchange. So let me show you Tenerife as an amazing environmental lab. Just a few facts. You know that Germany consists of 16 länder. I'm going to show. In the winter time, you have 16 landers plus Tenerife and Mallorca. So that's the Tenerife I'm talking about. So Tenerife is a quite tiny island. Just to give you some of the ideas, this Monday, when we started, we have 19 degrees in the south, where the tourist resorts. We have 2 degrees at the mountain and -6 at the summit of the volcano. You know, in such a tiny island, we have such a huge climatological, diversity. So this is one of the big ideas, big things about Tenerife. You know, the diversity in every different aspects. And look, within 20 kilometers, you may have such a huge diversity. In this case, in climate, but I'm going to show you the diversity also in other aspects. So the distance between Camp Linford, where we are, and Tenerife is around 3,000 kilometers. We have usually 3 direct flights daily. Okay, so the connectivity between the islands and Düsseldorf is very good because we are we have a good climate and the tourist resorts. Let me just give you a quick overview about this laboratory called Tenerife. The island is around 80 kilometers in length and around 70 kilometers in this direction. It's a volcanic island. You can see here in the middle this huge caldera, Las Cañadas caldera. It's like 20 per 10 kilometers. It's a World Heritage because you can actually find any volcanic feature in the world within this area. And in the middle is El Teide volcano. It's the 3rd largest volcano in the world. Okay, and there are many interesting features. We have at the corners of the island the oldest parts of the island, and they are really nice biological hotspots. We also have this is the Weimar Valley. It's a gravitational landslide. We have 3 of them: Weimar, La Orotava, and Icod. And most of the population are here, the local population. You will see where the tourist lives. The area of the island is 2,000 square kilometers. It's twice the Wiesel district, and Carlos is 1/10 of your tiny country. So we are tiny. Okay. If we can just have breakfast in the capital, going to the Anaga sector of the island, we have these landscapes. We have this sort of forest. We call that Laurisilva. Then we can drive half an hour, and we are already with the location of the pine tree forests. The Canarian pines is pine trees is a local species. Then we can go a bit further up. This is the sort of landscapes. Then within the Caldera de las Cañadas, these are endemic species. Okay, this is like 2 to 3 meters tall. It's called the Red Taginaste. And also the symbol of the island. This is the drago, the dracaena, and the Phoenix canariense, the palm tree, is also from an endemic species from the islands. So, and this is our local king, is the blue neck lizard. They are in different sizes. So Tenerife as a biodiversity hotspot, you know, within just talking about endemic species, we have 200 Canarian, 140 just from Tenerife, vascular plants, nearly 3,000 invertebrates, and 21 vertebrates, just endemic in Tenerife. So if you are students or you are interested, just know that we are a biological, environmental hotspot. Also, if you move from the tourist spot in the south, we have one of the largest cities, San Cristobal de la Laguna, where a university is host. It was founded in 1792, so it's new for the Spanish standards. And this city is a World Heritage because it was the first medieval town in Spain without defensive walls. Okay, so it was the design of the town was exported to America. So all colonial American cities have the same planning than La Laguna. That's the reason it's a World Heritage. The capital of the island is just 6 kilometers south. It's Santa Cruz de Tenerife. Okay, it's an important harbor. And in this picture, every pixel is a person dancing merengue and salsa during Carnival. It's like it's like the big party in Tenerife. And of course, the economy of the island relies on tourism. So the red spots are where the main tourist resorts are located. So are the basics of our economy and also the basics of our environmental problems. So we have to, find a trade-off between those aspects. Regarding science, what are we good in? Of course, in astrophysics, we have the Observatorio del Teide in Tenerife and the Observatorio del Roque de los Muchachos in the island of La Palma. Actually, in Tenerife, we have the largest battery of solar telescopes in the world. So we have the second, third, and fourth largest solar telescopes in the world. In Tenerife, the island of La Palma is actually devoted to nighttime astrophysical observations, whereas in Tenerife we have the solar observations. Biology, in particular ecology and marine biology, we are also good at that. These are the people in charge of the seagrass research that we talk on Monday. Of course, volcanology. There are 3 institutions in the island working on that. This is actually very nice field to work with you guys because we need instrumentation, students to go there. So this could be a very good idea. The funny thing is that we have volcanological research, but we don't have, like in biology, we don't have these studies at the university. Political fights in the past, and things like planetary exploration, for instance. We are also at the Las Cañadas del Teide. Many of the ESA and NASA rovers, are sent there to make some testing. So there are a lot of things that we can do there. So this is just a quick presentation about the island. So just let me focus on one example that we can work in the near future, because I believe it's very interesting. It's like the hidden treasure in Tenerife. So if you move from the tourist spots, there is a different island, and in particular, how we extract water is unique, I believe. So let me go on that. So this is the island. So all these colors areas are protected areas. Okay. So nearly 45% of the island, it has some kind of a protection law. Make the difference between we have a protection law and they are actually protected. Sometimes it's not the same, but we are trying. And on the left, you have the cultivation areas. Particular, the largest thing now are bananas. You have a picture on the top, and wine. Why wine? Because we have a certain local culture that everybody during the weekends go out for lunch, and they go for lunch just also to drink wine. So the only reason we are keeping that strong, cultural and economic liaison with the wine is because of that. Because every weekend is like going to church when people go to for lunch with wine. So this means that nearly 1 million people living in the island are squeezed in the land that, in the gray areas of this map. And they have to drink water every day. So where water in Tenerife comes from. Just let me show this picture. This is also this Monday. You see this layer of clouds. This is where the inversion layer is located that day. Usually the inversion layer goes down to nearly 1,200 meters above the sea level. Okay, so above the inversion layer we have a dry downward air that collides with the humid wind coming from the ocean. So we usually have this layer here, and this is great for astrophysics because above the inversion layer the air is really dry, so we don't have problems with making infrared observations. Astrophysics is not a matter of visible observation, it's infrared. So the lower the water vapor, the better for us. So this is a low resolution, but let me show you. You see Tenerife, and these are the clouds formed by the inversion layer. So you can see here in La Palma and a little bit in the island of La Gomera. So when you correlate, just remember the clouds here and these maps. Sorry, some of them are in Spanish, but you can see the rainfall rate correlates beautifully with the clouds in the inversion layer. And we also have a map here of the evapotranspiration and the average recharge rate, because all the water in the island comes from the groundwater reservoirs. Okay, these maps look really great, but actually we need to measure in more detail. But this is a big issue for us. I will tell you in a minute. So this is how the water system works in Tenerife. When there is a lot of rainfall, suddenly you see, springs, outcrops of water anywhere. This is because the island, the layers is very heterogeneous. So as soon as the infiltrating water finds an impervious layer, just goes out. So in particular, in the past of the island, let's say 100 years ago, this was the idea. We have a lot of outcrops, waterfalls that now just disappear because we are extracting too much groundwater. Okay? So one day you take the car, go to the above 1,000 meters above sea level in the island, and sometimes you find this sort of mining infrastructure. We don't have coal, gold. Why we have this stuff in the island? So if you go in this sort of mine, you see this water coming out. So let's step in the mine. You see, this is Don Andres, one of the persons working in this tunnel. So we start drilling tunnels until we reach the phreatic level. We don't have wells. We drill in the horizontal because the island is so steep that it's better to drill horizontal and not vertical. So most of the groundwater infrastructure comes from these horizontal mines that we call galleries. Okay, so we go in. You see that they are just. It is really dangerous to find water because remember it's a volcanic island. So from time to time you will find dikes. So if you just blow up the dike, you may find water on the other side, and all this water may come up. So you have to do it, carefully. So next time you go to Tenerife and take a shower, remember that all the water flows in this way. They drill until they find water. The big advantage of this thing is that once you find water, you don't need energy to transport the water because all the galleries are above 1,000 meters above sea level. And the cities are, in the coast. So just gravity makes the, the deal. This is the typical picture of one of these tunnels. From a scientific point of view, there is a lot of work to do here because for now, all these tunnels are private. Okay, this costs around €1,000 per meter drilling. So people just put money to drill until they get water, or maybe they don't get it. So so just telling these people, okay, may I go inside my blah 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 blah, saying, because people are, it's private stuff, so it's difficult to go in. So right now it's nearly impossible to access the galleries. But just imagine how much science we can do inside the. I will show you in a minute. It's unsustainable completely. So ideas, maybe just how to access the tunnels, some sort of robotic droning, blah 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 blah, because there's a lot of science to do here. And the other treasure in the island are these wells. They are called Canarian wells. They are 3 meters in diameter, and they can go down up to 600 meters until they reach the phreatic level. So it's a terrifying experience. One of these guys is me, and after 100 meters you just see nothing, and until you go down and you see here the water. And sometimes they say, okay, this is not crazy enough, so let's drill now horizontally. So yeah. So it's even from the point of view of like a museum, it's crazy, all these things. And this is the machinery, okay. And one thing is how to extract, and the other thing is how to, move all this water. It's sorry. So this is a map with all the galleries and wells in the island. All the lines are just the track of the galleries. So we have nearly 1,600 kilometers of tunnels within the island, and the amount of water being extracted every year is around 200 hectometers. Okay, this is what our consumption. And how to transport all this water is also private and done by hand. So just imagine these people with no knowledge of engineering transporting water. For instance, I bought water here, by my banana plantations are here. So I need some sort of pipe, with a given inclination, and it's done by hand. This is, for me, is one of the most amazing things. This is the, depending on the island, the amount of water. So in the case of Tenerife, right now, 80% of the water is coming from galleries, but this number is decreasing. So we have to go to desalinization. then you need energy to do the process and to transport the water to the cities. So this is you have to add this problem. This is the amount of water. You see that the groundwater is decreasing. We are already extracting the old water from the islands. So this is we know that this is going to be we are going to empty the main aquifer within years. So we have to move to desalinization or any other ideas. So from my point of view, this is just important because it is the water we drink, but can you see the amount of underground measuring stations we have in the island if we could have access? So just let me put it in dots. So this is scientific information that we are missing. Okay, and some of these dots are actually 800 meters below the surface. So this is a huge scientific, library that still can be exploited. So one of these ideas, just to give you if we just connect all the points where you can have an idea of the shape of the groundwater system. Every line is a 250 meter, okay? Look at the red line to see a vertical profile, and this is the problem. This is the topographic profile. This is the water level in 1925, and this is in 1997. Nearly 500 meters drainage. So, and this is, of course, when the gallery stops getting water, they re-drill. So they are getting to the old water system, as Eric, you commented. We can do, we would love to have new data to do maps like this. This is for the bicarbonates in the groundwater. Temperature. We have this obvious distribution. The north is colder than in the south. This is because of the volcanic activity, or it is something to do with the rainfall and blah blah blah. So these are issues to be worked. Just to finish, this is a very easy work we did a few years ago. Is okay. Let's take the red square area, and just let's take these galleries in this straight line and make a vertical profile. So this is going to be like our laboratory for this thing. There are so many galleries that we can choose and make vertical profiles. So we have these galleries, and S1, 2, and 3 are boreholes. So we are collecting some data. S1 is an amazing borehole. It's in the national park. It's actually an underground building built by the local water authority to control the infiltration rates in the center of the island. This is the only actual scientific infrastructure we have with water, but it's nearly impossible to get into that. Easier to go to the moon than okay. So this is a cross section of this vertical profile. You have the topographic surface, the impervious layer, and the wells and the galleries. So we can play, we can build a model, and in this case we are trying to see if the temperature could be a proxy to study groundwater circulation. So we can do profiles like this because it's unique in the world, because there are so many in such a tiny area that we can do this kind of games. So the idea is to see, okay, which data we do need to characterize the groundwater system. So we make a simple model. So okay, let's play with the porosity, conductivity, water retention, heat capacity, blah 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 blah, and make a 2D model of the system. the rainfall, recharge, and let's forget about this. So this is like the temperature distribution done with the model, and these are the temperatures collected in the gallery. Right now, we wouldn't be able to collect this temperature because the galleries are closed. So do we have any idea of how to collect this temperature without really accessing in the interior of the gallery? So these are open questions. So we try to do is, okay, let's start modifying the model to try to fit the galleries. So we started, okay, let's inject here the average geothermal heat flow of the planet. So they don't fit very well. So we have to increase the heat. Okay, this is going better. This is too much. So you know we can play with this thing just a game. Okay, and also change the depth of the impervious layer. So all this, you know, we can play with things, but we know with these models all the information we need. That is a lot. The recharge rate, the humidity of the soil, porosity, So there are so many things that we can actually measure, you know, that is a very nice and open laboratory for us to work with. So just to finish, within this issue of the water constraint, we have severe restrictions to access the galleries and wells. We need, this is the reason I asked for the power consumption. If we try to tell the people in the national park, can we actually install? No. But if we go with a low power hidden monitoring station that they don't, okay, could be a good idea. And also innovative ideas on how and what else we can measure. And of course, this is science, but there's also an open field on water quality, water distribution, etc., etc. And this is just with the water business. This is my last transparency. So remember, my island could be a great laboratory to study for our students to go there. Biodiversity, environmental sciences, we're talking about the atmosphere, the ocean, the groundwater, volcanology, very important for us. Smart tourism and astrophysics. Okay, so this was my presentation. Thank you very much. Carlos. Yeah, I didn't show this in the presentation, but we are also using INSAR images from radar imagery, and we see that there are two areas where the surface terrain is going down. It's a subsidization because of the decrease in this issue, and this is a very nice and open question. What are we doing with the magma chamber of the volcano? Because the water pressure is an important issue in yeah, exactly. So ideas like at the summit of the volcano, there is still fumaroles. Continue with the monitoring. There are changes in the water vapor, even in the chemistry of the fumaroles. And you remember that we go from sea level to the summit, 4,000 meters, in just 12 kilometers. It's huge. So any change in the pressure distribution could be really dangerous. Yeah. Yes, what we are doing right now is we, people in the island, monitoring through INSAR the stability of the island. They are about to install two gravimeters also to just to, and there's also an idea of using some kind of seismic signal also for this. So people are thinking of that, but this is a major issue. Yeah. Just it's El Teide volcano is classified as one of the 10 most dangerous volcanoes in the world. Not because it's a very dangerous volcano, but because it's surrounded by 1 million people. So there are already evacuation plans and stuff like that in case of an emergency. But you're talking about a long-term issue, so no answer. You know what that means. Uh, I don't. I Yes, I don't trust very much these numbers, these figures I gave you. There is plenty of room to work on, for instance, in the evapotranspiration data, and in particular also the rainfall, because there are very few monitoring stations, and people are relying too much in all data. But you're completely right. I don't trust very much these numbers, and the issue is that the government is making plannings for the near future, maybe with data that are not very updated. So. Hmm. Yes. Yes. Exactly. I completely agree. Hmm. Yeah. This kind of ongoing work, actually, the water authority, the new water authority, is actually more aware of the real scientific issues that lies behind that. Because if you say that, okay, 35% of the water goes to the recharge, is 35 or 12 or 50%? And where in the island is taking place. So right now they have they're aware of this, but there is still a huge open field for science to do there. Mhm. Yes, exactly. Yes. Mhm. Yeah. The biology we have been doing in Tenerife for the last 100 years um, is the classic biology. Still, we have to move on into new, monitoring with with monitoring stations and things like that. Go beyond just characterizing by eye, and so we need more scientific data in the biological branch. Yeah. Yeah. It's like a mesh of. Yeah. Exactly. There are, yeah, exactly. There is a. I completely agree with you. There are still a lot of very open issues, and one more important thing is that people from the atmospheric science divisions are realizing that due to the climate change, the inversion layer tends to go down. Okay, so we are not talking about thousands. So maybe also that the rainfall distribution will change in the future. So let's. Okay, thank you very much again.
energy storage devices because she had an appointment in the afternoon and I was short. So because we are running late as usual, we kind of switch the order of talks and she will present right now as opposed to the end.
Okay. Yeah, okay. Hello everybody, and yes, I'm sorry to change from nice Tenerife to electrochemical analysis. And yeah, to be honest, I'm also not speaking about electrochemical analysis, about environmental analytic questions, but in the first place about application in energy applications, mainly fuel cells. But I will also make a small excursus to bioanalytics. I was asked to introduce myself. My name is Irmgard Buder. I'm professor of renewable energy and electromobility. What do renewable energy and electromobility have in common? Any idea? Energy storage. You need both for renewable energy, at least when you cannot rely on hydropower, but you need to rely on wind and solar. You have fluctuating energy sources, so you need to store the electricity if you want to use electricity at night or when no wind is blowing. And for electromobility, in principle, the same. You need some electricity storage or you need an overwire. So as that, I'm electrochemist. I studied at the University of Saarland. I made my PhD in cyclic methods of electrochemical analytics. I changed afterwards to the Institute of New Materials and worked on the development of electrochromic windows using nanoparticles. Using nanoparticles brought me then to Gestacht, the Institute of Polymer Research, where I worked on the development of direct methanol fuel cells, specifically on the membrane development. And yeah, the target was to develop a portable direct methanol fuel cell for portable applications. From Gestacht, I went to ZBT Duisburg, working on fuel cells using hydrogen. And 2012, I started as professor for renewable energy. So, why fuel cells? Fuel cells are used and are supposed to be used in the future even more in stationary transportation and in portable application, specifically when energy density matters. So also, when you compare it to batteries, when you compare it to capacitors, lithium-ion capacitors, electrochemical capacitors, power density is much lower. Also here is the power density shown, here is the energy density shown. But fuel cells have the option, you can increase the energy capacity comparably easy, just by increasing the hydrogen tank. And in contrast to batteries, for batteries you need to provide both anodic and cathodic material. For the fuel cell, the cathodic material comes as free if you use air as oxidizing, or oxygen in air as oxidizing agent. So that makes it attractive for transportation. As in future, battery trucks would be very, very heavy, or you would need to charge them very, very often. No option for our today's logistic. So also here the idea is to use fuel cell trucks. Also, Duisburg, I just read in the morning, is planning now to substitute the diesel buses to buy instead hydrogen buses to be carbon neutral in the future. And that climate change is a pressing issue. Yeah, you have demonstrated the last days very clearly, and also today's talks were unfortunately showing it's very urgent to reduce greenhouse gas emissions. For stationary applications, Weiland, for example, is investing in fuel cells for stationary applications. Here, fuel cells have not a high efficiency as batteries. A fuel cell has an efficiency of around 70 to 80% in transforming chemical energy of hydrogen into electricity. But for stationary application, you can use the heat and provide, for example, hot water. So in principle here, in these applications, you would use both heat production and electricity produced. So last not least, for portable devices, when energy capacity is an issue, fuel cells can be an option. So if you have no chance to go to low energy consuming sensors, for example, then it might be an idea to combine hydrogen storage with small fuel cell and with a more energy consuming sensor or whatever application you have, which is more consuming. So, electroanalytical methods are considered as the most important branch of analytical chemistry. Stated by Maga et al. 2021. I'm very sure nobody agrees in this room with that, but electroanalytical methods have two advantages. If you have it set up, it's simple in execution, which can be a big advantage, and it can be miniaturized. So for example, last year, I had the honor to supervise a PhD thesis together with colleagues in Nijmegen. And here the question was, how can we develop a sensor basing on electroanalytics for dopamine? And yeah, if you want to go to living systems, then extreme small and extreme not invasive is of course an issue. So we have as electroanalytical methods potentiometric analysis. Measurement of potential difference can give you information about a sample. If you want to go quantitative, very often what you can do is colorimetric measurement. You measure the current caused by application of a constant potential, and at the end of the day, the charge you measure, also the current times time, equals the amount of electroactive species. So this gives you a very, very exact option, an option to measure very, very exactly also small amounts of substances. Voltammetric methods, I use cyclic voltammetry in my PhD, gives you an information about kinetics. The sample is here subjected to varying potential, and what you record again is a Faraday current, but more detailed information can be get by impedance spectroscopy. Here we can also apply a direct current or direct voltage signal. Also we can in principle use potentiometric analyzers or colorimetric analyzers, but the important thing is we combine it with a small alternating current or small alternating voltage signal. Why using a small alternating voltage or small alternating current signal? We can vary the frequency. And by varying the frequency from the range of millihertz, millihertz would mean the measurement can take several hours, because 1 millihertz means the amplitude goes over 1,000 seconds, to megahertz. That means we can measure at very, very different time scales. So, also in impedance spectroscopy, impedance and phase shift are measured depending on the frequency of an alternating current voltage signal. Also here in this example, if this is the voltage signal, then you measure the corresponding current, and depending on the properties of the system, you would observe a phase shift. So when you put that into imaginary and real axis, then the phase shift would here the angle between real axis and the measured complex impedance, and you have an imaginary part and a real part. So, and depending on the properties of the sample, now this impedance and of course also the phase shift would vary with frequency. So in the simplest case, that would be an electrode surface. This is the electrolyte. So also some substances are in the electrolyte, and when the working electrode has a certain potential against the counter electrode, then depending on the potential, also positive potential would attract anions, negative potential would attract cations. And what you get automatically is a so-named double layer. And this double layer in principle behaves in the first place as a capacitor. So we have a capacitor. When electrons make electron transfer, we would have an electron transfer resistance. And of course the electrolyte has a resistance too. So we have a resistance in series with a resistance which is parallel to the capacitor. And now, using equivalent circuits, how do resistances change with frequency? Not at all in the first place. Capacitors change by frequency. Capacitors would have a very low frequency at would have a very low resistance at high frequencies. They block completely when we have direct current or direct voltage. So the lower the frequency is, the higher would be the impedance of the capacitor. So at high frequencies, the current would go this way. At low frequencies, the capacitor increasing the resistance, and latest when the resistance is bigger than this resistance, the current would go this way, because the current always goes the easiest way. So that means we have here an information which can we also get depending on frequency. And what we get here for this equivalent circuit would be, at the beginning, low resistance, only this electrolyte resistance, you try to make that very low, can be measured. When we decrease the frequency, then it increases, and at a certain range it comes to a constant value, because then the capacitor is blocking completely and doesn't influence it. The capacitor is blocking completely, you see also in the phase shift, shown here as the axis. The phase shift has a maximum and goes then to minimum again. In the Nyquist plot, also imaginary scale against real scale, that would look like a half circle. And that would be in principle the simplest equivalent circuit showing an electrode. Fuel cells have two electrodes, obviously. Also at the anode, hydrogen is oxidized. Hydrogen releases 2 electrons, forms 2 protons. The protons move through the membrane, and at the cathode, oxygen is reduced. Oxygen is reduced to water, For this reaction, you need 4 protons and 4 electrons. Means in sum, 2 hydrogen molecules react with 1 oxygen molecule. So, to distribute a hydrogen, we have here something which is named flow field. That's, in our case, a graphite plate with channels in it, because we need also to transport the electrons. So, also the massive parts are for the transport of electrons. The channels are used for the transport of gases. Here the same. The gases are transported then into a so-named gas diffusion layer. That's carbon paper, which has pores, so that you have both electron transport and gas transport again. But the challenge is, you need also, to get a reaction started, to need the contact with something ion conductive, the membrane. And both reactions have some activation energy. You need catalyst. So also on the membrane itself, catalyst is coated, and only when gas phase, electron conducting phase, and proton conducting phase are in contact, we can have the reaction. That makes the construction of fuel cells also a little bit of tricky. So, both electrodes are interacting. We have here no reference electrode. That's different to other measurement methods where you try to get a reference potential. The only information we have in the first place is here the potential difference, what we measure between anode and cathode. In ideal case, 1.23 volt, usually lower due to ohmic resistance of the membrane, due to activation energy, and due to diffusion, because also you get here, the gases have to be transported to the reactive sites. So, also the only potential difference is known. Both electrodes contribute to the impedance. So that is our measuring cell. So here, this is in principle our fuel cell. Here you see gold-coated the electric connections, and the whole thing is pressed together with defined pressure. So Wagner, 2002, already measured impedance spectroscopy at fuel cells. You see here on this side the phase shift, you see on this side the impedance, and here the frequency in logarithmic scale. And also the figure doesn't look so different to what I showed before, but when you look closer, then you see that it's here already not symmetric anymore. So, also we have 2 electrodes, cathode or anode, with series resistance, membrane in this case, charge transfer resistance of anode and cathode, and capacitive behavior of anode and cathode due to the double layer structure. And we combine that, then we get this equivalent circuit. So what is not shown here is, obviously here you have also an increase in phase shift, which is not due to the capacitance, that's due to inductivity. You cannot avoid inductivity of cables at high frequencies. And we have here frequencies of 10,000 to 100,000 hertz. Also here, some inductivity is not shown in the equivalent circuit, but usually cannot be avoided at high frequencies. So we have this equivalent circuit. This equivalent circuit can be used for modeling or simulating the measured curve. Also what you see as points are the measured curves, and what you see as line is the simulated curve. And you see here at the beginning, that looks quite good. Here in this range you see also some deviations. So, but now, how can we find out which electrode is which one? So, and for that, what we do is comparably simple. Challenge one of the electrodes. Reduce the cathode flow. We would assume, when we reduce the cathode flow, that only resistance and capacitor related to the cathode would change. The membrane resistance should not change with cathode flow. Exception, we have extreme drying out, I come to that. but by reduction of the cathode flow, there should not something happen to the membrane resistance. And in the first place, we would also not assume that the anode is affected. So that are measurements made by an internship student, Tom Latour, in November. And he reduced, also here is only 40 milliliter per minute shown. He also measured 35 milliliter per minute, but then the impedance went at low frequencies extremely up. So for making the graph a little bit easier to see, because what you see here also easy, you have even at higher flows, 60 milliliter, 80 milliliter, 100 milliliter, you have an obvious increase of impedance. So as what you see, wait a moment, that was the wrong way. What you see here is that in the low frequency range, the cathode flow has a high impact on impedance, while here nearly no change happens. So here the same. Here you see the phase shift is affected mostly here. Here, yeah, again, not much effect because the phase shift is already lower due to, yeah, the capacitor is blocking. So Tom Latour simulated also the system that is now shown for the highest flow rate, the equivalent circuit, and he made it, of course, also for the other measurements. 35 milliliter per minute is shown as dark blue. Then orange comes 40 milliliter, gray 60 milliliter, 80 milliliter in yellow, and in light blue 700 milliliter. And what you see clearly here is that you have here in R4 is here. This resistance increases extremely with decreasing flow rate. Also here we have 1.6 ohm, here we have 700 ohm, a milliohm. 700 ohm, the fuel cell would be dead. 300 milliohm, 260 milliohm, 216 milliohm. As you see here clearly, this part describes the cathode, this membrane resistance, and then this obviously represents the anode, and you see here no change, no change, some changes here in the exponent. What I should have mentioned is fuel cells do not behave as ideal capacitors. Both electrodes are not really ideal capacitors, and to consider that, something named constant phase element was used. Constant phase element is in principle a system which is behaving between capacitor and a resistance. You have here in millifarad the capacitance, and depending on the exponent, 0.8 for the anode, it's mostly capacitive behavior but some resistive share. We have for the cathode 1, and 1 shows that it's behaving like an ideal capacitor. So also here we could show, obviously this is the cathode, and we could, what was expected, we could show the higher resistance is related to the oxygen charge transfer. So another experiment Tom Latour made was looking at how did humidification influence the membrane resistance. The membranes used for fuel cells unfortunately need some humidification to be proton conductive. You may ask, why is this an issue? The fuel cell is producing water, but the fuel cell is producing the water at the cathode side. For the proton transport, they need the water at the anode side. And depending on the loads, the diffusion of the water through the membrane is too low, so that you get an effect, low humidification, high resistance. And what you see clearly, the cell temperature was 80 degrees. Starting with 40 degrees, we had a very high resistance, which nevertheless already was decreased during the measurement. Reasons for that could be, we measured at 500 millivolt, that the current was at this, under these conditions high enough at least to get some humidification. And when you look here, the difference to 40 to 50 degrees is not much. this difference is very big. So when you look at 50 degrees, here obviously in this range it's constant, and it gets much better at 60 degree humidification temperature. As when the dew point of the gases is 60 degree, membrane is happy. When you decrease the dew point, then you get higher series resistance. And another thing, when you compare here, and when you compare here, you see, oh, also at low frequencies, there's a change. When it would be only the series, the membrane resistance affected, then you would expect that the curve here goes this way. But what you see here, especially here, the gap is much bigger, which indicates that obviously some of the electrodes is affected. Also the electron transfer itself is affected by the humidification of the membrane. So here it was expected that there would be a change, that the effect is here even more pronounced, at least for these two measurements, was not really expected. So important is now, simulations are not so clever. The simulation didn't stick to 4 is the cathode and 1 is the anode. When you compare the values here, 4 is much lower than 1. Obviously this is now the cathode, this is the anode. The membrane resistance stayed the same. So again, the simulation is shown for the highest humidification, and looking at what changed, expected membrane resistance went down with increasing humidification, can be clearly seen, but you see also that obviously the cathode is affected. The cathode resistance went down with increasing humidification. So this could be due to better conditions in the three-phase interface. On the cathode, oxygen reacting with the protons, which needs to be delivered, and without protons, oxygen would never be reduced. So here, that could be a reason, but it looks here also according to the simulation that the double layer capacitance of the anode is somehow affected, at least between these two measurements. Here, this is not really significant. So here, what we could show, in fuel cells, impedance spectroscopy can provide detailed information about membrane resistance, the charge transfer resistance of oxygen reduction reaction, and the charge transfer resistance of hydrogen oxidation reaction. Both can be used for also characterizing of new materials, for example, catalysts, membranes. We are working at the moment also on high temperature materials in the fuel cell rack, which would have several advantages, but also some challenges. And what I want to show last, not least, impedance spectroscopy is also a powerful tool in combination with other analytic techniques. And in principle, when you see it, here we looked at two electrodes which were treated in a certain way. You need catalyst platinum and you need the electron transfer. You can in principle also coat inert electrodes with other materials, for example biological materials. So when you want to set up biosensors, then you would have an inert working electrode, a support layer, and then you try to fix a recognition element on your electrode. So the idea is that this element would change electrical behavior, capacitive behavior, inductive behavior, resistance, when a molecule of interest comes. Here in between there's a selective film, but if the molecule of interest comes here inside, changing the properties in the electrode could be measured extremely exactly. So here that would be a very powerful tool, for example, for analytics in environmental field. Another option would be here, you have two electrodes, you have here area recognition element. And yeah, depending on what comes to the recognition element, measuring here the current between the two electrodes, then you get very exact information about what is in between. So what you would need additionally is, as in the first place, you need something biological of interest. Nucleic acids, proteins, antibodies, cells, bacteriophages. You need electrodes or other devices, but I would concentrate here on the electrodes. And of course then, for the engineers of us, signal processor and readable output. But that would be also something you could set up, for example, for environmental analytics. Also here, Hussein has published this diagram in a publication about analysis of COVID-19. COVID-19 was at least in 2020 a very hot topic. Unfortunately, we know. These are my references, and many thanks for attention. And do you have questions? Is not, and the tricky thing is you need a load which needs to be able not to interfere with the impedance spectroscopy. Also we used a Sana potentiostat, and this Sana potentiostat is able to measure up to 3 ampere, 10 volt as far as I remember, but to be honest, the 10 volt you will never see in a single cell of fuel cell. And the electronics, yeah, so the electronics were started to develop around the 2000s by Sana. That's mostly proprietary knowledge, but in principle, it's one big system which is able, on the one side, to handle a certain amount of currents and voltages as DC, and then to analyze by frequency analytics. Yes. Yeah, so the DC points were 700 millivolt and 500 millivolt. In this shown measurements. Also usually you can operate a fuel cell, also open circuit voltage is around 900 millivolt, 1 volt. And you can operate them between 300 millivolt and 800 millivolt. And then we used in our measurements usually 5 millivolt amplitude. Also the measurements were made potentiostatic. Also, it's at BT where I worked before, we usually worked galvanostatic because then you can better provide the stoichiometries of the gases. But to be honest, our small cells needs already some flow to get also then rid of the liquid water, which is produced in a fuel cell. Also we have thought about it, but to be honest, up to now, also the inductance is quite high, 1 microhenry. On the other side, it's in a range where the fuel cell is not reacting. Also the fuel cell, the ions are not fast enough that you get much more information in the big megahertz applications. Also we can measure, when we go back, also we have no problems to measure the series resistance. Also here, the series resistance we have no problem to measure, and in principle here starts to become electrochemical relevant. Depending on what you measure, getting rid of the inductivity of the cables could be a big issue.
Would that serve also as a sensor?
Naja, the first question is the Lachgas has the nitrous oxide has the big disadvantage in the first place. It would go out as gas out of the wastewater, wouldn't it? Also the problem is, of course, also how do you force something to go to the electrode? And when you are in a liquid system and you have only some gases, then difficult. Also, I know you you use systems to measure oxygen content in water, colorimetric methods usually, but in this case you have high oxygen content usually, and I hope the laughing gas is in much lower concentrations as the oxygen. In gas phase itself, tricky. As you need some, what you need is some electric conductivity, you need some electrolyte. If you can attract a laughing gas, if you know the laughing gas would be attracted to something, then that could be an option probably.
Yeah, that graph I found it very interesting. At higher frequencies, the impedance increases. Do you think the reason is because the ions are not able to respond, or not?
Here I'm afraid it's mostly the cables interacting with each other. We try to reduce that by treating them in a certain way. Coaxial cables doesn't help in this case. Coaxial cables would make it much worse. Here that would be 3 kilohertz. 3000 hertz, 3000 changes per second. Electrons can do that. Ions start to vibrate on the double layer. So here, electrochemical, at least in the fuel cell system, I would not expect much, but of course, it depends on for what you are looking. If there are no more questions, then many thanks for attention and having me. Thank you. Ja, irgendwie habe ich mich mit der Brille verhakt.
Okay, so hello everyone, my name is Sina Navid and I'm student in information engineering and computer science. Currently I'm doing my master thesis in LatiNet on real-time web application for decision support in groundwater management. And I would also like to introduce Dr. Philip Hone, and he's over there. He's my supervisor in LatiNet. Okay, so groundwater is the essential resources that we have, and we utilize it in a wide range of purposes all over the world. But groundwater needs to be managed correctly in order to retain it as a resources. So in order to manage the groundwater, we need that the groundwater management measurement the groundwater level. But again, the measurement of the groundwater level is a more difficult and costly if we want to compare it with the surface water. So the pilot area in my project is LatiNet region. As you can see in the picture, this is the LatiNet region. LatiNet is a a public company that was founded in 1913 in Camplin-Ford, and they are responsible for groundwater, precipitations, wastewater and surface water in the left side of the Rhine River from Krefeld to the Netherlands border. So here is a Krefeld, and then here is the Netherlands, and here we have the Rhine River. So their tasks have become large and more diverse over the time, and since they have so many precipitation stations, groundwater stations, and pumping stations, they are providing a large variety of a wide real-time data source. But also, I would like to introduce one of the biggest challenge in this region. As you can see in this picture, we have some buildings in here. Here is the surface of the land. We have the maximum groundwater level and minimum groundwater level, and there is a difference between the surface land and groundwater. And in this region, we have mine, we have salt mine and core mine. So problem of mining is, problem of the mining is land subsidence. So the land subsidence, simply because of the mining, the consequence of the land subsidence is that the water just raising up to the building, to the basement of the buildings. So what's the solution? The solution of the LatiNet was something like that. They just drilled the land and just installed a water pump, and they started to pump the groundwater from here to somewhere else, usually to the nearest river. So with this solution, they want to protect the building that in here. And this challenge and this solution is the point key of my thesis, because we wanted to create a system that in this case is web application to assist the groundwater management, that again in this case is LatiNet, to know how long and when they need to operate the pump. So the project aim is, first of all, creating a web application, creating a temporal interpolation from non-continuous station, and I will explain what is the non-continuous stations later. Also visualizing the spatial interpolation and visualizing additional information on a dashboard like precipitation, pumping stations, and forecast precipitation. And the main framework that we have used was Python. Also, because we wanted to create a dashboard, we used Plotly Dash, and since again we wanted to create a map, we used Dash Leaflet, and both of them, Plotly Dash and Dash Leaflet, are the packages in a Python. Okay, so temporal interpolation. There are two types of groundwater stations in a LatiNet region: continuously observing groundwater and non-continuous. So this is the continuously observing groundwater level. It means that in a station that we have, there is a sensors, and the sensors can measure the groundwater and then send the data to the database, store it in the database each 15 minutes. So as you can see, for example, between 2018 to 2022, for this station 3001H, we have so many groundwater measurement each 15 minutes. So this is the continuously stations, and the non-continuous station or manual measured simply means that there is no sensor in there. So the people of the LatiNet should go there, measure the groundwater manually, and then store it in a database. So as you can see in this picture, between 2018 to 2022, for this station number 218, we have only 6 manually measurement. So the idea is to create a temporal interpolation for these kind of stations from the nearby sensors stations. So we have used the multivariant linear regression to fill the gap between the measurement that we don't know anything about, that there is no data in here. For example, between here to that one, there is no data, and we want to fill the gap with this algorithm. Then another thing that we wanted to do is spatial interpolation, and we have used IDW, inverse distance weighting, and in this technique or in this algorithm, we have three most parameters. And this one is power, smoothing, and max point. And with each one of these parameters, if we just play with them, we can create a new raster file. So the idea is to find the best combination between of these three parameters. So, and what is the best combination? Simply best combination means to have the most accurate raster file. So, and how we can understand the accuracy, we can use the error things. So in here we use RMSE, or root mean square deviation, to find the lowest value of RMSE. So when we find the lowest RMSE, then we found that the accuracy of this raster file is the most one, and then we can use this one. So this process was a long process, and it took a long triangles, some rectangles, and as you can see in each one of these is just represent of the different raster files. So the first one is groundwater level raster file that we have produced previously. And then the second one and third one is surface elevation and land use. Both of them are provided by the state of North Rhine-Westphalia. So surface elevation is just this, we can find out the surface elevation of this region. But the third one is land use. So the land use simply means we wanted to know the use of the land. We wanted to know that if we have a land, for example, in here, what is inside, what is on the land, what is on the surface of the land. So like a building, is it a tree or is it a forest? Is it a just farmer, agriculture, field, something like that. So there are, I think, 11 categories for this land use, and LINEC has a different threshold target for each land use. So then we need to just combine these two data together to create another raster file, like a target. So simply in a target, we can have the land use of each places in a region with the threshold target. For example, for a building, the threshold for the target threshold is 3 meters. So it means that LINEC doesn't want that the water just exceed these 3 meters. Because they want to protect the houses. So then we wanted to create another raster file, which is target level, and target level in here is produced by subtracting the target from the surface elevation. So if we just subtract these two raster file, we can get the target level. And this target level is exactly level that we need to save this distance between the groundwater to the threshold that we have. Then the last raster file, which is the most important one, and we wanted to load this one on a dashboard, is deviation target. So the deviation target, again, is produced by subtracting the target level from groundwater level that we have produced previously. And then we got this deviation target. And this deviation target raster file, we can colorize it to the different color. And for example, I will show it later, but if it has a color, then we can say, okay, for example, the red one means that we are near or we are exceed the threshold, or the blue one is we are far away from the threshold, from the target. So we want simply understand that we are near to the threshold, to the target that we have, or we are above it, or we are below it, or if we are below, how much do we have time, how much capacity is still there. Okay, so the first thing is web application dashboard. As you can see, this is our web application. This is web application because I have run it in a web browser, but unfortunately in here I'm not able to just run it in my computer because we are not accessing to the database and server of the LINEC from here. But as you can see, this is a screenshot of our dashboard. On the left side, we can see the main map. We can see the region LINEC. We can see the 6 pumping stations in here. Also, we have some buttons over there, like a groundwater, precipitation, and forecast. And whenever we click in each one, we can get a new information loaded on a dashboard. Then we have the line graphs of each 6 pumping stations over time. For the pumping rate, we can see that which pump works over the time. Also, we have the groundwater level in here that it's connected to one of the station in front of the pumping station for now. Also, we have another slider in here that we can adjust the time. So simply we can drive into the time with this slider. Okay, and there is also 2 tabs over there, pumping stations and Rasto. Whenever we are in pumping station, we can see this kind of information. And whenever the people just click on a raster file, they can see the deviation target raster file that will be loaded to the dashboard. So then the result of the temporal interpolation. Now this is the result of station 42. So you can see that in here, the line, the black line is a real groundwater measurement that was manually. And then with the help of multivariate linear regression, we got the predicted measurement. And the blue one is predicted measurement. And as you can see in here, in the most of time, they are overlaying each other. And then we can see in another chart, we can see the perfect line of linear regression. If everything was 100% correct and accurate, all the points should be on the line, but unfortunately it's not possible for all the time. So you can see some of the points are above the line, some of them are below the line, and the last one is just show the error. So you can see that the error of this for these stations, it's less than 25 centimeters, which is acceptable, and most of the errors are between near to the 0. And this is only for station 42. And don't forget that we have more than 200 stations, but right now I just show 2 of them as an example. So this is another station, station 526H, and you can see in here the error is a little bit more than the previous one, but it's still less than 50 centimeters, which is still acceptable for a LINEC. Okay, so in here we have a groundwater level raster file, and this is the video that has been created over the time. You can see that the time is just going in the 2022. We can see the groundwater level in spatial interpolation, and you can see that we have like a flow, we have a stream of groundwater from the highest one, which is there, to the lowest one in there. So it's nearly 25 meters, and there it's near 15 meters. So also you can see the stations in here. There are 2 types of station, estimate and measured. Again, the estimate means that we have estimate with the help of algorithm that we have. So it was the non-continuous one, and the measured was that the sensors stations, the sensor that was continuously. So we can see how the groundwater just changed over the time. Okay, so I'm going to the next slide. If we are stop here, we can see all the for each days in year of 2022. And then the next one, which is the most important one for LINEC, is this one, the deviation target. And in here again, we can see how far we are from the target that we are. And then this is the important one, because for example, the blue part, it means that we are in below of 4 meters. So it means that we have 4 meters until to reach to the target that we want. And the red one, we don't have red one in here, some pink one, so it means like 1 meters above the threshold. So in these places, like here and in here, these places, of course, over the time now, for example, in July of 2022, we know that the LINEC should take action to do something, and they need to start to pump, because in these places they are above the threshold, so they just exceed the target that we want. But for most of the places, we can see the color is blue. It means that we are below the target, and some places it's like more than 4 or 5 meters. Like here, that you know, in here we have a hill, and that's why that the color is completely blue over the time. But yeah, now the time is in December 2022, and then we just loaded this one on a dashboard. So with the help of this raster file, so the groundwater management, in this case LINEC, they can simply see at the first glance that where they are near to the target or not. If they are near to the target, or if they above the target, they need to take action. And when they are far away from the target, they can stop the pumping, or they can just let the pump stop. Okay, so we have created web application dashboard with the below information: temporal interpolation, spatial interpolation, and groundwater deviation map. And additional information as well, like a precipitation, pumping station, and groundwater forecast precipitation. And with the help of this system, we can assist the groundwater management to reduce the energy and cost, to reduce the overall pumping, and to manage the groundwater level more precisely. Because if you remember, I talked about this one, that measuring the groundwater is more difficult and costly if you compare it with the surface water. So we can manage the groundwater level more precisely because we can see the map in a first glance to understand that how's the groundwater level in each places, in each location of the region. So, yeah, thank you so much for your attention. Yes. Yeah.
Why do they spend this much money to pump out this much water so that it's 4 meters below the target?
Okay, yeah, actually this is the aim of the project, because they want to know that if they are far away from the target, so they can stop the pumping. They don't need to do the overall pumping. So that's why I said we can reduce the cost and energy, because you know the pump is just working with the electricity, so they spend so much time, so much cost, and you know the energy as well to just pump, and most of the time this pump is just overall things. Yeah. No, the aim.
Maybe I can also add a comment to that as I work for LatiNet. So in some regions it's just topographically driven, right? So we have natural like depth to go that exceed our target. So there's no regulation that we require to do in some regions, but they're still part of the map, right? So in some regions we're outside of the loop of one of the select pumping stations that we have. So we still have that information in here. We don't have the tools to change the ground level at that specific region. But overall, it's still a tool that we can use for understanding where, you know, where we need to take action and where we can actually relax action to maybe reduce pumping costs. But not in every place of the map, like we're actually like enforcing something.
Okay. So it's not everywhere.
Exactly. So yeah.
So it's just a specific point.
We're really not trying to pump much more than we need to.
Okay.
Just in some cases.
Okay. And what are the red parts where you have to pump?
Exactly. Well, this is still like sort of developmental. So in some cases, this might also be regions that are close to a river, and so we need to sort of match information about where the actual targets are. We haven't reached that point yet. So some of those regions that are red right now, they might not be protected by us. We'll have to look at that in detail. This is just a tool that we require to do that.
And this dark blue thing, this is the
This is a hill.
Hillside, right? So the natural topography is high, and then in that case we have quite a large depth of ground, and that's why it's open. So everything's fine in that region. That's the local thing.
Yeah.
You mentioned the manual of how well the linear regression matches with those few six-ish number of measurements.
Yeah. As I mentioned here, so we just check this one, for example, station 42 or the other one. These two stations are completely manual. So we just create a temporal interpolation and then check it. And that's why we have the error bar like that one, to understand that how correct or how accurate is this algorithm.
Pretty stupid question. Have you tried in continuous monitoring stations to do a proxy of non-continuous monitoring?
Yeah, that's why. Yeah, we are using that one to just. We're using the continuous stations, continuous sensor station that are in the nearby of the non-continuous stations. Yeah. In the first slide. Which one?
One of the first ones, which are like showing the continuous
Oh, yeah, this one you mean.
measurement. Is this, yeah.
This one. Oh, that's because of the pumping, because, just the groundwater raising, and then they started to pump, so it's just decreasing. And then again, stop the pump, it's increasing, starting the pump, just decreasing. And that's why we have something like that.
And why it's so low at the beginning? Is this a mistake, or did they just did not pump?
You mean in this year? It's a good question. Maybe Philip can answer it.
Can't say specifically for this one. I'd have to check it out. But probably there's something related to us having installed a pump at that time.
Yeah.
I worked there for so long, so I don't have all. It's got to be the other way around, right?
Yeah.
I think we reduced pumping somehow because the number was rising. But I can't say specifically.
Okay.
Thanks a lot for this very nice talk. Just a quick cosmetic thing since we are looking at slide 10 and 11. So
Slide. Oh, yeah, this one.
compare the two, I would suggest on the next slide not to connect the dots.
Oh, okay.
Because, like, yeah, here we see that the limit is actually regulating
Yeah.
level, yeah, and then we have variation in between. But if you go to the next slide, then yeah, it doesn't make sense.
Yeah, you mean. Okay. Yeah, thank you. Okay.
Was there a specific reason to use the simplistic multivariate approach? Seems to work,
Mm-hmm.
but you are not considering any spatial effects, do you? So usually this is a hydrogeological application. You would expect kriging or geostatistics, right? Have you thought about this, or would that add any value? Because if the simplistic approach works, it's fine, right?
Yeah. Okay, so for now we are using that algorithm, IDW that I said, for the spatial interpolation. But of course, for example, in the future scope of this project, because this project is an ongoing project, so it's part of this project is my master thesis, but it's not finished project, so it's a big and long project. So maybe in future, they can use also the other algorithm to just check that which one is better, and also the effect of the spatial things on a spatial interpolations.
By the way, I would like to introduce Höhn. He's not just working at LatiNet, he's I think one of the leading hydrologists there.
Yeah.
Right, and another question I have is, so especially the red areas, right? These are the hotspots, or supposed to be the hotspots. Did you cross-validate it? So is there a measurement with which you can say, okay, it's really a red spot?
Even in
Because
here.
we are also currently developing simplistic groundwater wells to basically to increase the density of the measurement networks, right? So we use the simple probes and pressure probes and use the LoRa data transceivers here to the tower where we installed the LoRa bound gateways. So I hope that we can basically maybe fill some information gaps which we have here. And the question here I have is, you see there are these red spots
Mm-hmm.
supposed to, basically, so that they are a cost of taking actions, but make sure that these are really red.
Exactly. Yeah. We're not yet. So this slide, this actual image is 1 day old, so we haven't cross-checked yet. But I'm well aware of your senses, and I hope that in the future we can, for instance, equip those stations where we know from the data-driven approach that the estimation is. There's some that are good, some that are poorish,
Yeah.
and I think it would make most sense to equip those that have poor estimation with sensors, and specifically those that are poor that are in these kind of regions. So I think we're just in the process of identifying those regions, and then the next step would be exactly as you said.
Yeah. So when we talked about the idea of his master thesis, I remember that we also talked about, or had this idea of proactive pumping to increase the retention capacity of the catchment. But this is not part of this thesis yet, right? So basically, you also, because one thing is basically to protect the houses and the gardens and everything, but another thing is generally also to provide enough retention room in your catchment to be able to somehow store heavy rainfall events, right?
Exactly. It's not hard, but it's related, because it's the
which means there is enough space for new master thesis. Right? Thank you so much.
But the overarching idea is of course to reduce like heavy loads of pumping.
Great.
But we just need the tools to do that.
Yeah. And maybe a very final remark is that it depends on your application, but geostatistics, as you said, right, you want to reduce the error variance and so on. Usually when you use standard interpolation mechanisms, whatever you use, you're underestimating the variance and the uncertainty in the field. So it depends on whether you use this for let's say a follow-up risk assessment, for example. Then I would highly suggest to use simulations, right? So random experiments. So basically, instead of using interpolation, that you do a statistical simulation of the system. Okay.
Yeah, okay.
Thank you.
You're welcome. Thank you so much.
I would like to change the schedule again. Christoph, do you think you could present now? Would that be possible for you? So it's okay that we maybe postpone the talk after the
Ich habe schon, ist alles schon da und
okay.
Auch das ist mit dabei.
I'm afraid I cannot really introduce Christoph Thomas sufficiently well. Maybe you can introduce yourself. I would really love to. So as I said, he's a guest who came on short notice because we wanted to discuss a few things on this ongoing research idea and project idea of this flux. And as Christoph is a renowned specialist in measurements of fluxes by all means, you can say, but especially with eddy covariance methods, right? But it would be great if you introduce yourself.
I'll say a few words. So thanks for having me. Unexpected little talk. I've known about this for about 2 hours that I was supposed to give a talk, so I just cobbled together a couple of slides. So don't expect any skyrocket results, but this is basically what I had in my little portfolio. So typically what I do I titled this Disco in the Woods because we use light, we use sound, and we use fog to simulate flow, to analyze flow, to quantify flow phenomena. So very general, we investigate transport dynamics, and this often has something to do with turbulence at this air-plant-soil interface. So I'm at the University of Bayreuth, and I am a professor there, but I also have an affiliated appointment at Oregon State University, actually, where I spent 10 years of my life, and 8 years ago, 2014, I returned to Germany. Okay, it's difficult to get people excited about turbulence. Maybe this is a little different in this audience because you're a little techie, you're a little geeky, that's good. But sometimes people are like, why do you need to study turbulence? It has so many excellent properties that I'm not going to talk much about. It's truly three-dimensional. You can't understand the vorticity. It's chaotic. It's stochastic, which gets a lot of statisticians excited about it. It has a multiplicity of scales, so we need to say how large are these transporting eddies in the air. It's dissipative, so it needs a mechanism to be maintained. Otherwise, it's going to die. But the last one, if there's any ecosystem scientists of you, you should be getting excited about this. It's very efficient in mixing and transporting, and hence turbulence timescales are the ones that really matter for most processes. Okay, what do we do? This very nicely connects to what Eric was talking about. So there's a lot of biology happening, right? Biological processes inside these forests, photosynthesis, evapotranspiration, dark and photorespiration, so all these respiratory components, and you had a very nice sketch about this. As a fluid dynamicist, as a micrometeorologist, you don't really care about those. You say, well, it's happening down there at the small scale, but what I really would like to do, I would like to put a surface on top of my system. Currently do not consider the sides, and we can do a full 3D mass budget, but we typically simplify to 1D approach and say, anything that moves through my upper lid of the system, this is basically the net exchange, right? And what you basically do is that you count all these eddies going up and down at very different frequencies and different sizes, and you just do a very simple budget. Anything that goes up minus what goes down, this is the net flux, right? This is basically what Eric already explained. This is basically the approach for most sites. But the nice thing, you may think micrometeorology disregards all the complexity of the biology, and the biologists typically are not happy about this, right? But what the micrometeorology does is that it provides a control because it provides forcing, so it provides wind speed, and wind speed creates turbulence, and turbulence keeps gradient steep, so stomatal gas exchange is tremendously important. It transports, it gives you light, precipitation, so there's many things that actually matter from the atmospheric forcing onto the biological process. So not just one world doesn't care about this one and we simplify everything, but there truly are very many biological processes that are responding to the micromet forcing. So what my workup does, we investigate these interactions about the plants, the air, and the soil, and it's not really about only the air or only the soil or only the plants, but it's really about these double-sided arrows. And micrometeorology is a really difficult word to pronounce. You can do this at home in front of your mirror and you can say it 10 times over, but we even add this biomicrometeorology, which makes it even more difficult to pronounce. Okay, and only if you can pronounce it without any difficulties, you can actually graduate from my work group. So what do? So we do, typically when I try to give like a 2-minute talk about what we do, is that we do the 3 T's. The 4th T would be my last name, Thomas. Okay. 3 T's, transport, trends, and tools. And as you can tell, this is a temperate rain. Actually, this is a dry forest in the eastern side of the Cascades, so North America. We also do these 80 covariants. Can you actually see this? Yeah, you can. Wow, you don't see it actually in here. So on the screen, so we do these infrared gas analyzers. In this case, it's an open path instrument. It's a very dry site, fire-prone system with a sonic anemometer, and we do monitor those. And I just want to give you a few pictures of what are the kind of studies that we do. So we ask very simple questions. The transport, we say, well, how does air actually move? Right? I mean, if you have a flow that interacts with flow obstacles, and for us, it doesn't really matter whether it's a tree or a house. There's a bluff body, so the air can go in or can go around it. So it does interact with a pressure field, of course, but it's a flow obstacle, a tree, right? Again, a biologist would probably disagree. How does air move, and how we do a lot of work currently in urban areas, and the city of Bayreuth, also in the city of Munich, looking at urban canopy street flows, and of course there's difference between being out in the forest and being out in the canopy layer with built houses where they have a lot of these bluff bodies. So a lot more pressure interactions of the flow with it. So very simple questions: transport, how does air move? How does the turbulence respond to the presence of flow obstacles? But then we also ask, well, it's nice to have these targeted experimental studies where we look at fluid dynamics, but what really matters often is if we observe those over a longer time, right? And this is over 1 year carbon balance for a forest ecosystem. Well, how much breathing, so how much exchange, how much carbon does you actually sequester? This is kind of a nice plot of something similar that Eric showed. So this basically gives you the day of the year, so 1 to 365. And this gives you the hour of the day. So you get these Hofmeter plots. Basically, you see the respiration at night, and you see the uptake, the negative NEE during the day. So basically you can tell, well, of course, something is happening here. So much low carbon uptake. So why is this happening? There's a drought, in this case, a drought stress happening. So we use our information about what turbulence transports to answer the questions, how does this carbon exchange actually change? And here we also spent some time in the Antarctica, which is perfect because there's no trees, there's almost no biological life. So it's a purely physical laboratory. It's just ice and rocks. Awesome. As a physicist, you like going to a laboratory. We have very controlled conditions. And then we also go to Costa Rica, or you go to the Amazon, where it's the opposite. You only have these, trees and critters happening, which really complicate the processes. But so we ask questions like, how do the answer dynamics for a Costa Rican flux site in Santa Rosa National Park impact the water carbon cycle for tropical forests? In this case, this is a dry tropical forest. So not all tropical forests are wet forests, as you know. Is Antarctica warming up and starting to exchange carbon dioxide? This sleepy landscape has been frozen, stored away for a long, long time, but the circumpolar vortex is also transparent to the warming signal of the rest of the Earth. And of course, there's dramatic changes to the ice being buried underneath these glacial tills. And how do the drought affect ecosystem functioning? So this is certainly a big question that we're asking for many systems. May it be in temperate forests, may it be in boreal forests, or may it be in tropical forests. But then we also are engineers. We like to play with things, as some of you do, as I noticed. That's great. And so it's the last piece about the tools, the instrumentation. And the question that I'm asking is, well, we often rely on point measurements, right? I mean, we just had a classic example, how to interpolate. But interpolating is cheating, right? It is. I'm not criticizing anything, but it is cheating because you fill information that you do not have. The question is, well, what if we're able to create a sensor that actually continuously monitors a certain variable? So we do really have a tomography of our environment, and we're so reliant on these point-based measurements invoking ergodicity of the process and saying, well, it is as good to observe in a process at one location over time as it is to take snapshots, which in ergodicity is a fundamental assumption that we assume we never validate. So so I said, well, this is a problem because we like to study turbulence. So we started looking into this, and it's been about 10 years. And we're spearheading the deployment of these large fiber optic cables arrays we call fiber optic HARPs. Just an EU consolidated grant project just ended essentially 2 weeks ago. I was funded by the EU to build up these large fiber optic HARPs in the ground, in the air, to then measure and visualize spatially turbulence. So basically you have 10, 20, 30,000 measurements every 10 centimeters, every 1 second. And then really when turbulence comes to life. So this is a lengthy path that we took over the past couple of years, basically the last 10 years. And you see just pictures of an experiment in a mid-range mountain valley in the Fichtelgebirge down in Bavaria. Or we also have deployment in the polar night up in the Arctic at 80 degrees north, where we put these fiber optic HARPs into the snow and essentially study the snow and heat transport across the frozen ground, permafrost, snow, and then air layer. So this has been very helpful of deciphering the exchange, analyzing the exchange with true spatially observed measurements. I won't go into any of the details how this is actually done. This uses Raman backscatter for those who are familiar with this term. What brings me here today? What brings me here today is a summer school that we actually held now twice in 2019 and 2022 at the Panguana Research Station. This is the oldest privately run research station in the tropics in Peru, and this was actually funded by the DAD, so it's a perfect match. So twice, and 2022, and there we essentially, 2019, were able to install a couple of sensors and brought 10 students from Bayreuth and 20 students from Peru together. Intense exchange, cultural exchange, but also, of course, scientific teaching, always in the context of climate, cycling, carbon, energy, and water in these tropical ecosystems. And this is a map where it shows the location of the Panguana Research Station. So one of the peculiarities that Eric didn't quite mention is that this Panguana station, you know, Andes Flux, we had these 4 dots over here, Tambopata would be over here, and there were 2 up here. It is tucked in right between the Andes chain, but also there's the El Sira mountain chain, and this makes this location really being different because it's tucked in between 2 mountain chains, and the precipitation is even higher than the rest. Very nice. The South American or South Atlantic and South Pacific highs here. So we have a very specific setup of the atmospheric circulation, which then gives rise to these precipitation patterns in the dry season. And so when we went there 2019 for the first time, we set up just a very simple microweather station that actually communicates via cell phone. So we're high up on the mountain or high up enough on the mast to catch a cell phone signal, and we do get data transmittance. And this is now over about 3 years precipitation, cumulative precipitation, and this very nicely confirms what Eric mentioned. It never really stops raining, even though you have wet seasons and dry seasons technically, specifically because you're right up against the Andes mountain chain and the Sierra, it essentially never stops raining. There's a bit of more of an increase during the wet seasons, but also in the dry seasons you get significant precipitation. As you'd expect in the tropics, wind speeds are really weak, which makes it very exciting. Why? Because it's the turbulence, the exchange is primarily produced by density differences, very large scale eddies and very weak winds, so very little shear, which makes it the opposite of what the Arctic actually experiences, where the turbulence is really, really tiny. Buoyancy kills your turbulence, and it's just only shear-driven turbulence. I think as a physicist, you're excited about looking at these end members of the spectrum of the forcings. At least I am. Wind directions, awesome, you can see nothing. Why? Because the wind directions turn around the entire 360 circle every day. It's just a very regular clockwork pattern. It has to do with local pressure differences against the Andes. It's really nice. I'll see some frowning on Eric's face. I'll show you a couple of, we do have some preferred wind directions, but at this location, if you just plot out basically the 10-minute data, you basically see nothing. The daily pressure amplitude is tremendously small. It's only 15 hectopascal. The daily amplitude is almost as large as the entire annual amplitude. So for the meteorologists among you who are some background, this is a very small annual amplitude of about 20 hectopascals even across the year. Here in the in our latitudes reach easily 70, 80, 90 hectopascals. Temperature, I think we're in a tropics, so it's very warm throughout the year. And also you don't see a big change between wet season and dry season. Okay, so what brings me here is that we would like to, since we do have we have a nice collaboration with the Panguana Research Station, and we've been there for about 3 years with this microweather station. We would like to bring one of the Andes flux sites in collaboration to this. So we used our observations from the 3 years and ran a flux footprint model. So basically this is a very simple Gaussian statistics that you basically run and say, well, where does the wind come from? How far, tall are you? And some assumption about the turbulence. And you basically see that you do get some preferred flow direction. So basically here, what you see is the isopletes, so the lines of probability from which area of the landscape is seen by your flux measurement sitting at the cross. So here I have observation system over here, and the turbulence instruments typically look, upstream, because this is where the informations come from. However, turbulence is truly three-dimensional stochastic. Some information comes from your back, of course, as well. But we do get a preferred wind directions to the northeast and the southeast. Okay, and you can do this for different day and night cases. But you see, you do have some preferred wind directions here, and this is good news because you see the underlying satellite image. Land use. So even though this is primary rainforest, people like the forest, they like the resource, they like to extract woods, they like to grow cattle. So of course, there's a lot of little farms that eat into the primary forest, but we're still basically within this intact forest. One of the things that we got excited about also is that close to the site, and this is a picture from a drone taken looking southeast from the potential tower location, is that there's a small aguajal, so an area that is a wet spot. And a wet spot, so you have saturated water, this supposedly can produce a lot of methane. So thinking about the carbon balance, we do not only have to think about carbon or carbon dioxide, but carbon also potentially may mean here methane. And if you combine this, so the aguajal is basically located here, very close to the tower site. This is within the higher probability where the signal is coming from. So we certainly also have to think about adding a methane sensor. I know that's more costly, but down the road, I think we'll also have to consider not just CO2, but also methane. Okay. Since you mentioned this, give me a nice little door into saying advertising our summer school or spring school on flux and turbulence. We do offer this every year from our university. There's international visitors who come and learn about how to process these eddy covariance measurements. And this school really is all the way, it's a one-stop shopping. This year it's only 10 days long. Typically it's 12 to 14 days. It takes you all the way from designing an experiment, setting up these instruments, collecting the data, analyze, interpret the data, and write the report. So it's one-stop shopping. And this is what it's meant to be. This gets used by as a training summer school by a lot of groups. And the general topics are setup maintenance, analysis of energy and carbon dioxide exchange. We vary the instrumentation depending on what you're interested in. You can come with your own needs and say, I would like to learn about fiber optics, I would like to learn about ground-based acoustic sensing. But the typical kind of the classics are, we set up an eddy covariance sites with 2 different heights, net radiometers, weather stations, soil moisture and soil temperatures, and then typical questions like energy balance components, carbon balances, and so forth. So we can actually then construct these, at least over the 10 to 14 days observations, we can set up these or measure these ensemble averaged diel fluxes. So this is really what we're good at, I guess. This is the extension to the ecosystem sciences, while of course our interest also is in analyzing the turbulence, and there's, depending on what you're interested in, you can also learn about spectral analysis techniques and all these things. The flux itself is a product of statistics, of course. Eric mentioned it, it's a covariance, but of course there's much more contained in the data that you can think of, and this is of interest to us. Right, that should be it already. Of course, it's not me actually doing the work, but a lot of the students who do the work. And thanks for giving me the opportunity to introduce my group briefly. Thanks. Yeah. This is NEE in micromoles per square meter in second.
And there it's 15, the green is 15, that means 15 micromole CO2 stay in the ecosystem per square meter.
This is the actual flux. So this is the NEE computed from the vertical turbulent flux plus the change in the storage term. Okay, it expressed in over this 30-minute period. So basically you have 17,520 pixels in here because it's 365 days times 48. Okay, so you have these 17,500 pixels, and every pixel is this is the average 30-minute flux that you have.
What I think is really interesting, I mean, at the leaf level, if you measure photosynthesis, net photosynthesis, so what gets in and what is used by the leaf.
Mm-hmm.
So you have was 10 micromole per square meter per second. We have this discussion already. So it is in the same order of magnitude. So that means that the whole ecosystem of the rainforest is not storing more than one leaf. It's just one leaf layer.
Okay, so this is not a rainforest at all, right? This is a coniferous. This is a coniferous. Basically, no. This is a ponderosa pine site east of the Cascades. Okay, so this is a fairly dry ecosystem. So it's very open, LII of 2.4. So it's very open, a lot of light. So this is 50-meter tall trees. So it's ponderosa pine, very fine and fire-prone species. The GEP is about 2,200 grams carbon per square meter per year, okay? And respiration is around 1,800, so you have a net balance of about 400 grams C per square meter in year. What Eric showed for his Tambopata site, this was about 5 megagrams carbon per hectare per year. So if you convert this into the same units, you arrive at 500 grams per square meter in year. And this side is about the same. So basically, if you compare those two numbers, so right, this is integrating over all the pixels. So if you compare those numbers, this side is just as inefficient. Well, but you had release, you had net source. This is a net sink. So this system stores 400 grams of carbon per square meter per year, while this side, according to your observations, release 500 grams. So of course it heavily depends upon the moisture regime. This site is basically snow-fed and has most of the exchange in the early part of the season, and then you enter what you'd mentioned. This is exactly the stomatal closure, right? This site runs dry, and the trees just cease to do their photosynthesis in the morning. Here in the late afternoon hours, and then the drought becomes so severe that they don't open at all. So it's just limited by this. So you need to integrate, in order to get the annual budget, you need to integrate the flux across the entire year, of course, and then basically take out the carbon out of the CO2. Well, I guess the leaf, I mean, if you look at, if you look at net photosynthesis, so if you really look at this, net photosynthesis, NPP is different than NEP, so you need to factor in the autotrophic respiration. And then for NEE, you need to fill in the heterotrophic respiration. So I think the carbon balance is different. It cannot be. I mean, it can't be that the carbon balance of a leaf is just the same as the entire ecosystem, because the respiration is much smaller. Well, okay, you need to consider one thing. Maybe you're looking at the leaf carbon balance during light conditions. The leaf does not only experience light, but also dark conditions, right? And then if you integrate the flux over the 24-hour cycle, and then you have, of course, here, the annual cycle of the light availability, this also changes the entire thing. So if you look at a peak, so if you pick the right time of the year, yes, you can make the NEE of the ecosystem work the carbon balance of the leaf, but that's cheating, because to integrate over the entire balance. Okay. Okay, okay. There's the classical big leaf approach where you can basically model the entire forest, and that is the big leaf approach for open forests applies fairly well. But as soon as you get into the shading, if you look at the diffuse radiation, there's many things that then basically invalidate this. But I mean, this is why big leaf approaches worked fairly nicely for a long time. Then we realized for open forest that's true, but if you then move into multiple layer canopies with a different heat regime and moisture regime, you really can't, even with a two-leaf approach where you have a shaded leaf and a sunlit leaf, you get yourself into trouble by, if you want to model this. Yeah. Okay, so you just mentioned about the green dots. Yes, no, this is similar. Yeah, of course it is. And remember, this is always, the net exchange that integrates over all the things and all the sources. And that makes it statistically very challenging because ADE can be almost a zero difference between two huge components in opposing directions. But that's the exciting part. And so you need the ecophysiology and you need to do the partitioning into even our net fluxes. I mean, there's techniques to partition the net flux into photosynthesis and respiration in order to get the actual ecosystem functioning. Just the net sum, I mean, this is the one number that you really want to have to take into the current climate change debate. This is what everyone pays you for doing, but you don't really understand the system. The number is just too aggregated. So you need the ecophysiology, and this is why we need still the biologists. That's the good news. Low wind velocities. Yes.
So that means that U star would be still within measurable range.
I don't think that U star is a good way of assessing coupling. Just because in the tropics you are close to the tropical convergence zone and you just have no horizontal pressure gradient that drives any. I mean, if you look at the Navier-Stokes equation, the pressure gradient term is the main force that drives the winds. There's just no pressure differences in the tropics. And hence, turbulence is not driven by shear, but it's driven by buoyancy differences. And I think so U star is a very bad indicator for coupling in the tropics. But we have, there's many different ways, other ways, I think more meaningful ways of assessing coupling, whether your system integrates over sinks and sources. And when I looked at your nice peak in the morning, when the canopy space is flushed, I saw the very small flux, about 2 micromoles square meter per second at night, I said, there certainly is something going on. You're probably missing a large part of the respiration. Anyway, but I guess there's, but that makes it exciting, learning about how the turbulent exchange works. And the tropics are inherently different because the generating mechanism of the turbulence compared to the temperate forests and the Arctic. Well, if there's a forest. Sometimes there isn't.
Final quick question. So, to understand more about plant physiology, would you think it would make sense to combine these measurements, potential measurements now in Panorama with solar-induced fluorescence?
Yeah, certainly. I mean, we've looked into this, we've dabbled into this at Oregon State University. I think you can learn something about this. Certainly. I mean, having some estimate, even though you do get some spatial representation with a flux footprint, here even though you collect observations at one point, you always measure an entire footprint, right? This is what we call the footprint of the flux. So it always comes from a certain area, and you can run statistics where this is from, but you never see the entire area around your tower. You're limited by where does the turbulence carries the signal to your sensor. And I think to have a spatial idea about how different this is, this could be a very nice technique. I think anything that carries it into the space and doesn't just make up data, but actually measures, some variability, spatial variability. And this is really what we truly lack. We lack spatial variability information. So this would be helpful. Yeah.
Thank you very much for this brilliant talk. So, break. So
You let me know. You let me know.
So I think we're about to continue. I know the social part is the most important part of all, and that's why we don't have an online meeting.
Hello.
And that's why I really respect it if people take a bit more time and then we just run a little later. We can live with it, I guess. So we have Carlos presenting our something very different, and we are amazed how many different colors there are. So this time he's giving a talk on polarization. Let me see, I can find it here. Predictive model for the availability of phosphate in soils. Again, you know colors already from the woody colors.
Not blockchain this time, but could be coming soon. Could be cool. Thank you. Not blockchain this time. So I am the Linux guy again. So please install Linux instead of Windows. Okay, this is a great pleasure for me to share a very little small research, which is more like an open-ended case because this is not finalized yet. It is in the process. We have some findings, and I'm going to share them with you. This is my name. I'm with the Catholic University of El Salvador, and here it is, my email, in case you want to be in touch, ask a question. We are willing to cooperate as well in anything you want, so you can take note. Thank you. So this is the predictive model for availability of phosphate in soils. Problem is very easy. Soils of my country are pretty low on phosphate. It doesn't happen in Nebraska, which is the area in which I studied my master's. Those are very high in phosphate, but very low in iron. We have lots of iron, but not phosphate. Well, actually, we do, but it is not available. That is what happens. So, as we know, all of us need phosphate in our cells because that's the way the mitochondria recharges itself. We get phosphate from grains and meat, but it comes from plants, and it comes then from soil. So what happens when we add some kind of manure or some kind of chemical fertilizer? Not all of the phosphate is going to remain available immediately, or, well, what happens through the time? Is it going to be blocked by the complex of exchange of the clays of the soil, or is it going to be available? Who knows? Who knows, because every soil is pretty different. I can see here in Germany, soils are soft and fertile, but in my country, I mean, soils are pretty heavy. If you take a little piece of soil and you throw it to someone, you kill him. It is hard because geologists say that our soils are young. That's what they say. And they are volcanic, so they are, pretty hard and pretty heavy as well, not soft at all. So what we did is this. We have, because of the clay complex, we have a lot of soil acidity. And that acidity, what does is to trap the phosphate ions and join it to the exchange site of the clays. So the phosphate is not available for plants. And this is one of the most limiting factors of crop productivity in our country. So we can add some chemical fertilizer like the ammonium phosphate, the AP, and that's what we did with this little experiment. We took a very small area. As you can see, this is kind of small. This is a sugarcane area, and we took some spots, some samples. Well, first of all, sub-samples, and then we took a main sample for each of these, and we took them to the laboratory to study how could the field respond to phosphate amendment. This was not intended to be just a mere little bit for helping plant. It was intended for amendment to correct the problem. But how much phosphate is necessary, and well, how much is it going to last? The only way to know it is running an experiment. And what we could find is great spatial variability, and we did computer semivariogram analysis. This is actually the first one. This is about the pH. I'm not sure if you are related with this term, the spatial variability, but what it means is that this is not a common stuff. This is not a common graph in which this is X, this is Y. No, what this means is that the data is related, for example, here at 6 meters of distance. If I have one sample of soil here, its response to chemical treatments is going to be similar to the others within the range of 100 meters. That's what a semi-variogram means. I don't know if I am blocking your sight. I'm sorry. I will try to use the pen of the computer. I don't want to block anyone. So this area, these points between, let's say, from 0 to 200 are correlated, but that's a small part. What happens with all of these other data? They are pretty dispersed. They are pretty much dispersed. So they don't have the same kind of response. That's what it means. So I can estimate that responses are similar between mostly 200 meters. That means a lot of variability in our soils. You can have a field, and one common mistake that we do is that if I have several hectares of a crop, I will apply the same fertilizer amount to the whole crop, and I will run into inefficiency, fertilizer inefficiency, because I don't understand how the variability affects the absorption and the availability itself. So this is only for pH, but as I told you, pH affects the availability of phosphate. So in largest distances, less correlated effects. So there are some other semivariograms. I have here this one over here. This is the effective cation exchange capacity, which is the ability of the clays to absorb some fertilizer cations and give them in exchange for other cations. One of the main actors here is calcium. For example, clays can absorb calcium and then release phosphate in exchange. It can happen quickly or not, depending on the amount of organic material and some other elements present in the soil. Even aluminum, which is not a fertilizer, it is toxic, but aluminum interferes in the process. The acidity, the soil acidity, lowers this effect, but here we have a problem. As you can see, the data is very dispersed. So the sample responses are not correlated. This is kind of senseless. This is not a regression line. It is a graph trying to find a nugget to range a number of samples that could have similar responses, but this is completely lost. There is no correlation in a small area. This is the important stuff. And a small area in my country has very high variability, spatial variability. So now, what we did is that we took all the samples and we distributed in 3 subsets of each sample, and we applied the different doses of DAP, the ammonium phosphate, and we were
seeing how it changed the phosphate availability through time. For example, this P10 variable, what does it mean? We added some amount of phosphate and we saw the response of that same availability after 10 days. Much of the phosphate was still available, but we had this response. Kind of better response, kind of more correlated information, but not much. Probably a little bit correlated from 0 to 200 something meters, but not much. That is kind of, let's say mediocre, but this is not mediocre, this is nature, so let's say variability. You cannot call mediocre to nature. Mother Nature knows. But what happened with the same samples 20 days after? Was still present the phosphate in there, available for plants? Present? Yes, it was there. It didn't evaporate, but probably it was not available. So here we had some attempt for correlation, but still data is very dispersed. We don't have something beautiful, well, quite beautiful, at least something beautiful like this. Here we have correlation. This other thing, no, it's awful. But in the other analysis, we had this problem. After 20 days, responses are not correlated, even in the same field. So in order to improve the amount of money which is going to be invested in fertilizers, in trying to focus for use efficiency or to reduce waste, we have to consider that the whole small area is completely variable. It's crazy. That's how it behaves, corresponding to phosphate in my country because of the clays, acidity, and the other things. And after 30 days, we have this. We had a little improvement while the phosphate was kind of settling down. A little bit of correlation here because we have a nugget, so between the range of probably 150 meters, we have some correlation, but the other information is kind of correlated. So what does this mean? That the classical statistics doesn't work at all. Regression here doesn't work at all. It is not useful. Nature doesn't care if kurtosis, skewness, and mean are very nice mathematical methods. They don't work. Like, for example, the original soil test showed that we had a 4.6 pH, which is low, typical of acid soils like ours. That is very typical. This is not an non-typical soil. Most of our farmlands are like this. And, well, we have a very good content of calcium, and this is also important. We have a lot of calcium, but still we have very few available phosphate. How is it possible with that much of calcium? Because of the acidity. It is about the size of the clays. And we also have this enemy here, aluminum. And we have some sodium. Sodium is not in a dangerous range, but aluminum is about 80, which is not good at all for crop producing. We have very few zinc, but as you can see, iron is okay. So major concerns are about phosphate. And all of this is not useful at all. For example, let's see the effective capacity of cation exchange. This is the mean, 10.25, but the variability is about, it's more than 8%, and the minimum and maximum range between 9 and 12, and we have some kurtosis, some skewness, so it is not very representative, and all of these data are very crazy. For example, we have this mean over here, the phosphate availability in the samples after 10 days, 10 days after treatment in the laboratory, not in the real soil, not in the actual field. We have this 54 something, and the range at the same time is 46 something. The variation could be very near to the average. So this is not useful. This is not useful. There is too much variation. That happens. It could be happening in Nicaragua as well. Could be. Our soils are kind of alike. Should be. We have the same geological history. Maybe. Yes. So I think I made the point that these descriptive statistics are not useful to study these kind of problems. And then what we did is that we used the Kriging algorithm using QGIS in Linux, sorry. And we produced, sorry for that. We produced some maps, but these maps are not really trustable because of the great variability. So Kriging algorithm did the best approach for interpolation in creating these maps. And they are kind of alike. They are kind of trustable because we don't need, for this application, millimeter precision. In that sense, this could be acceptable. Not excellent, acceptable. There could be some better alternatives, like probably machine learning. That's why I told you this is an open-ended case, because I haven't yet got into the machine learning. I have done some small things, but I haven't applied it yet, probably next time. And what I have is, well, this is the altitude, not really important at this time. This is the availability of, no, this is the pH, I'm sorry. Actually, the places with a little less altitude has a different, have a kind of different amount of acidity. Pretty normal. Those soils, water accumulates, and some sediments settle in there and change the soil chemistry or biochemistry. This is the exchange capacity, and this is the response of phosphate. From approximately 4 ppm, it jumped to 23, 26, 24. It doesn't seem to have that much variability according to Kriging. From 23 to 26, it is not that critical. That is why it is considered acceptable, even though it is not quite precise. What happened with the, oh, let me see. Yeah, P0. Let me see. Oh, this is the initial, this is the initial state before fertilizer. This is the, like, let's say natural circumstances. And now here we have the information with fertilizer. 10 days after fertilization, we measure the phosphate availability in the samples, and we feed the information in the database, and we simulate the field. We didn't touch the field. We touched the samples with GPS coordinates, and we are like mimicking, faking soil results. Like what happens if I exceed a doses with some chemicals? I don't harm my field. I just have some samples, do whatever I want. I can even harm the samples without harming the field. That's the point. And we had this kind of response. After 20 days, it remained kind of the same. And I was quite surprised that they didn't vary much. For example, here, 57 to 54 after those 30 days. There is not much variation, probably because of the quality of the fertilizer, probably because of the amount we added of the fertilizer, because we added something like 200, well, the calculation came from the estimation of adding 400 pounds of phosphate to almost 1 hectare, which is a lot for an amendment. It is a lot. But it seems kind of stable. It is a lot of investment to do because phosphate is very expensive in my country. Very, very expensive. But it seems that it kind of corrected the problem. And the effect was durable through the period of 1 month, which is the critical time for a crop to absorb phosphate. At that time, plants, since they are born to probably 30 days after, they are requiring mostly phosphate than any other, well, nitrogen as well, but than any other nutrient. After that, when they become reproductive, or when they become old, they absorb less phosphate, and they start absorbing more potassium, more calcium, more boron, if they are in the reproductive state, and some nitrogen as well. It depends if the plant has limited growth or non-limited growth. It depends on the variety of the plant. It seemed to work. It seems quite satisfactory result, but still we have some doubts with the accuracy of these maps because of the dispersion. However, we have the idea that the overall area had kind of the same response. So the chemistry of the soil was not damaged due to the fact that we added a lot of phosphate, and that amendment could work. That is the conclusion. Further steps, feeding that information into machine learning to have more accurate results, of course. This is why this is an open-ended case. And this is the very small contribution of what we did. Basically, what we wanted to do is to try an alternative for correcting a soil problem without actually harming the real soil, just working in a lab with samples. That would be it. Do you have any question? Oh, tell me. Sorry. Excuse me. Oh, thank you. Thank you. Please, again, I'm sorry. We made the sample for 30 days, not more. We didn't have more time. Yes. We actually did, but it is not included in this slide. I didn't want it to make it that large, but we obtained kind of similar results. So this is like the most important to me because this is like the attack dose. But they were kind of correspondent. And I think that's probably because the soil was so needed, I mean, lacking so much phosphate, that any amount you can add seems to be like an aid. That is my assumption, of course. But there is a lot of biochemistry in between. Okay, somebody else? No one else? Okay, we're done. Yes. That is correct. For example, some people, what they do is to add more calcium in order to release phosphate because calcium is cheaper. And surprisingly, the soil is so acid that adding more calcium doesn't really change much the availability of it. Yes, but it kind of remains the same. It is altered just a little bit because of the acidity. So that's a cheaper alternative. And as you can see, there are some things we don't have to worry about, like, for example, magnesium and iron. So we don't have to add. Actually, adding more iron in our soils, that is poisoning. Yes. Oh yes, this is a problem. This is counterattacked by adding more calcium. Aluminum is going to react with calcium and it's going to be decreased. And in exchange, phosphate is going to be more available. That is a cheap solution. But still, we need phosphate. Probably less, but still needed. Okay, something else? Somebody else? Well, I'm not a geologist and I cannot remember that data. It is supposed that the continent originated separated from Europe and South America, from Africa, and in between Central America just appeared because of volcanic activity long after the split of the continents. So that's why they say that we are having very young soils in geological terms. But the thing, what I can really see is that our soils are very heavy, pretty dense, and pretty sticky. They are very plastic. But your but your soils have okay, but your soils have undergone mineralization because of frost, defrost, frost, defrost, and we have kind of the average temperature the whole year, so there is not much meteorization by abiotic stress. That is could be, could be. But the other thing is that we still have some volcanic activity, and it changes a little bit the area. We have had some eruptions like 500 years ago, and that puts some sulfur and some other compounds into the ground with new layers, and that is actually still changing. Me? Okay, thank you very much. The soils, yes, and when you think that you have a mature, fertile soil, then a volcano throws ashes, and that changes everything. And then you go back to zero. That's what happens. Thanks to Ilopango volcano, that was the last one that changed our soil chemistry like 500 years ago. And that affected Nicaragua as well. Well, thank you very much then.
Really? Ah. Okay. Yeah, we already talked about LoRa a little bit, and Jan will explain to you our development chain, so how we do it ourselves. Usually we are building our data loggers and the sensor integration and the software and the databases and so on ourselves because we like it. What is it? And so and also Jan explained a lot about LoRa. I'm afraid I don't have a slide with me, but the sensitivity of this protocol. So you have LoRaWAN and you have LoRa. LoRa is the physical layer, and LoRa stands for long range. And it's a special encoding of signals, right? And what you have is a frequency modulation, and it's a chirp spread spectrum for those of you who know about electrical engineering. So the idea is that you have a center frequency of around whatever 868 megahertz in Europe and 915 in Latin America, or 2.4 gigahertz is a new system, and also 433 megahertz in some regions of the world. And these are bands, frequency bands, which are free to use, and they belong to the group of ISM bands, industrial, scientific, and medical, so they are free to use. That's the reason why we use Wi-Fi everywhere, 2.4 gigahertz, right? And so the signal encoding is really, so you are increasing the frequency. I think I can paint here, couldn't I? Harley, can you help me how to use the pen and all the stuff? It's here, right? And I would have to switch how? Oh, that's easy, right? So what you oh, that's easy. So what we have is here a frequency, and here is time, and you have a modulation which looks like this, right? So you start at some frequency. So maybe this is 2.4 gigahertz or something, or let's say 868, and then some megahertz here, right? A little higher. And what LoRa basically does, it keeps this pattern, and then you have some jumps in the frequency, and it ramps up in a different way. So this is the fundamental carrier, you can say, and the bits are encoded by breaking this symmetry. But you know this underlying pattern, which allows you to search for it, which means this signal can be even down in the noise floor, so below, let's say, so the signal is within the noise, and you can then use basically this sawtooth kind of modulation pattern, which you then move around in your noise, and at some point you see then a strong correlation, and then you know, okay, now I'm hooked on the signal, and then you can decode the signal and pick the signal out of the noise floor. Right. So this is one, and one difficulty is, so this ramp here. So the speed for the ramping is called the spreading factor, and you have spreading factor, for some reason they start at 7 to spreading factor of 12. And the spreading factor of 12 means the ramp is much slower, and this increases for some reason the signal to noise ratio. But as you can imagine, since you need one of these ramps to transfer your information, it takes longer. That means when you are very far away, you need a high spreading factor, which gives you a higher sensitivity of your system, but at the same time it lowers the bit rate. And what you typically have is, let's say, 50 bytes payload, right? This is quite a typical payload size for LoRa. And then, as Jan already said, this is just a physical principle, and then on top of that you have this WAN, which is wireless wide area network, a wide area network, which then does the synchronization and the setup of the network on a more higher level. For example, when you have a LoRa sensor or a LoRaWAN sensor, all gateways which are around you, which are in reach, would receive that signal, and then you are not binding to a certain access point as you do with SSID and Wi-Fi, right? What is the Wi-Fi name? What is the Wi-Fi password? You don't need that. So you are sending, and all of the gateways which are in the reach, in the range of sensitivity, would then receive the data, and all the data, which is highly redundant, of course, it's then sent to a network server, or the application server basically, and the application server then receives a list of identical messages, but with different, let's say, signal strength indicators, SISIDs. And usually then the one with the highest signal strength is then used, but they contain all the same message because you have 5 receivers or so. And one of the application servers and network servers is basically TTN, the Things Network, and that's a community-driven stack, yeah, we could say software stack for network servers and application servers. And what you do is basically what you need in your LoRa sensor. If you have a sensor, you have basically an application ID, which the sensor then binds to. In the end, the sensor is part of an application. So not part of a gateway in between, so you don't care about which gateway, which secret of the gateway. You don't need that. You just need you have to set up your own application, and then the sensor is then basically kind of paired with this application. Is this correct? Somehow. EUI. Okay. Yeah, but you have to bind the sensor to your application. That's what I said. Yeah. Okay. So and Jan will explain to you one example how we develop these LoRa WAN sensor transmitters, you can say. And then we would offer you, if you like, we can play with a system which is called, how can I erase everything here, Harley? Which one? Ah. Oh. Okay. Okay, and some of these here? Okay, but this is a simple eraser. Okay, but okay. Right, which is so we would have a little workshop if you like, and we would use Tasmota, which is a firmware for ESP kind of microcontrollers, and I think the one we are using today would be 8266, and this ESP microcontrollers, they have a Wi-Fi stack included, so you can use them as a Wi-Fi client. What is specific about Tasmota is it is a firmware which you flash on the ESP, and then the ESP opens a web server, so you get an IP address. So in the beginning you need USB to connect to the ESP 8266 board, which we give to you, and then what you will get, you do this with a software called Tasmotizer, and in the end you will get an IP address when this thingy here tries to bind or to connect to the Wi-Fi, and then you get, I don't know, what is it, 192.168. Oh, that works. And I don't know, 2.15, 14 or something, right? So you would get this IP address. With this IP address, you can use your browser. When you are in the same Wi-Fi, you could use your browser and parameterize the Tasmota system, which means you would have a list of potential connections and a list of sensors which you could connect to your general purpose input-output things. That means you don't have to program the microcontroller, you just have to configure the microcontroller. And that makes it very easy, and that's great, for example, in a context when you work with school children. Maybe we had 2 weeks ago a nice workshop with a lot of with a group of students here, school students at 9th and 10th grade, and they don't have a background in IT. They have a background in chemistry, physics, and biology. And we set up a wireless sensor network together with them for environmental monitoring. And that was so easy, right? So, and they really liked it. There were a lot of girls, and they understood also the beauty of, let's say, these systems. And then that's something, something we want to try to maybe convince more young people to study STEM and IT so computer science in particular. Great. So I think Jan, you can. If you like, Jan gives an introduction to what he's doing, and if you want, you can do a hands-on training with this motor later on your laptops if you want. Okay? Does that really work? Wow. That's usability, right? Okay.
So, ja. Das weiß ich, das hat Wiki irgendwann mal gemacht. Das hat das Doku-Wiki mal irgendwann gemacht. Ja, das hat das Doku-Wiki irgendwann dazu generiert. Ich glaube, das ist irgendwie, irgendwas mit dem Bild hat das zu tun. Ich weiß auch nicht, warum der das so gemacht hat. Ich habe keine Ahnung. Das hat er bei manchen Bildern gemacht, bei manchen nicht. Keine Ahnung. Aber das ist nur in der Detailansicht. Das heißt, das hier ist das eigentliche Bild und wenn du da draufklickst, dann kommst du dahin. Ja, ja, genau. Alles gut hier, das ist die Caption. So, this works. So I want to show a bit how we develop our LoRaWAN sensors. And as an example, I brought something, and we can go outside and have a look at the thing in person later if we want. So let me open the package. Yeah. 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 Yes, I can show that as well. So maybe I will show now what we use, like the ESP that Rolf just explained for. And our workflow is very similar to what we do with our LoRa sensors, just the LoRa just needs a lot more programming. And the Wi-Fi stuff is a bit more flexible. So this is what I did before. So we made a trough automation. I think I explained this as well in the IoT lab. And this board is custom designed, and it also works with the motor software you will see later. And with this you can actually actuate stuff and sense stuff at the same time. So what we did here, we used it for trough automation, so you could automatically empty out the whole trough. So that new fresh water comes into the trough and the cows would drink it again. This is especially important in the summer when the water is warm and the cows wouldn't drink it because it's too warm. No one likes to drink warm water, basically. So with this, you can see here we have an actuator, and this is a temperature probe, a DS18B20 to be precise. And the housing is completely AP68 or 67 waterproof. We never had really problems with this. So yeah, actuation and sensing at the same time is possible, and everything is connected through the cloud basically, but you could also do it locally. So in theory, with what I will show you later, you could build this. And actually, this started out on a breadboard. And then later it came then to the PCB. Yeah. So what you will see right now is the dendrometer. So how the dendrometer works is fairly simple but patented, unfortunately. So as you can see, it's directly at the stem of the tree, and there is like this rubber bands going around, so the tree can still expand and retract and basically grow. and then there is this push rod, and in the inside of this dendrometer is just a potentiometer. So you can measure the resistance and then calculate how far the push rod is pushed in. That is the whole principle. That's it. So the idea is if the tree now grows, the little push rod here is moved into the sensor, and then the resistance changes, and that's what you monitor. Yeah, they're very with this. So this is a DC4. They are from Ecomatic. They are in Munich. This one we have a range of 1.6 micrometers, but this is just dependent on the ADC, so analog to digital converter, basically. So if you have a very precise analog to digital converter, you could be more precise even. But this one can do up to 50 millimeters, but they also have a smaller version, the DC3. This image is unfortunately a bit dark. Half the range, but therefore if we use the same analog to digital converter, we get double the not precision, but resolution. So with this we can actually get sub-micrometer, I think 0.8 micrometer if I remember correctly. And I think, what is now going around, I don't know where it is, or is it already back, is a DC3. Very simple, and therefore it's also not that hard to really read out the sensor, which makes it easy. It's very power efficient to do so. Now I want to show you how I started the whole development. And now I have to think about how the camera app on Ubuntu is called. It has a very... It was like Smile or something. No, it was not Smile, it was... Let me check. No, it's not called Camera, that is the whole problem. It's called Cheese, yeah, of course. Of course it's called Cheese. Now, let's check. Yeah, you can see something. Maybe I can make it a bit brighter. Fully. So this is how the whole development started, basically. And I will explain the whole mess now in a bit more detail. So how this all works. First of all, okay, we need a microcontroller. So the microcontroller is the black board over here. And to be more precise, the whole microcontroller is under this green package here. Can maybe show it a bit better. A metal shield, yeah. So this thing is shielded. Okay, it will not get sharp, as it seems. Ah, there it is. And you can already see it's called a cube cell. It's from a company called Heltec. And the special thing about this, it's a complete system on one chip. So in the end, you can buy this module, and you will have the same pinout, just without like this LED, the micro USB stuff, the USB to serial converter, without all of that. So that makes it very easy to prototype with this board, which I can just put into the breadboard, and then program the whole thing, and then I just need to turn it into a PCB later. It's just easier. We had some problems, to be honest, with this chip before. It's not the holy grail, as you might say. What is good about it, you can program it over the Arduino IDE. This makes it very easy for us because simply we need to read one value, or maybe two, and send this over LoRaWAN. We don't need any fancy programming in this. But we had some trouble with older sensors, older I2C sensors. Most of the newer ones we tried worked. That's all you need to know. So just to be aware, if you buy these, some of the sensors you maybe used to don't work, but what we tested is I think DS18B20, like a temperature sensor is working, or most of the temperature and humidity sensors work as well if they are not 7-8 years old, but maybe you don't want to use them at all either way. So I put this board here into my breadboard. Does everyone know what a breadboard is in general? Okay, now I expect everyone knows what I'm talking about. So with this breadboard, I can make easy electronic connections with like these jumper wires. That's all you basically need to know. And then I thought about, okay, what do I need to do to attach the sensor and read it out very precisely? So for that, because it's basically a resistor value that I need to, or a voltage that I need to measure, I need an analog to digital converter, because as you might know, like a normal microprocessor only understands zeros and ones, but I want all the stuff between that. I do not want to measure 0 or 3.3 volts, I want everything between that. So what I need is an analog to digital converter. Actually, this chip already has one inside, but it's not the best. It's mostly used to measure like a battery voltage that doesn't need to be really precise. You just need to know, okay, if I'm close to the end of the battery life. So I thought, okay, I need something externally and also something very precise. So that's what this thing is. Okay, now you cannot see it because the chip is on the other side, but imagine there's a chip on the other side that is an analog to digital converter. And what this can do, it's basically a 16-bit analog to digital converter, which is not the precisest you can get, but this is what what Ecomatic, the company that built the dendrometer, recommended. You will need to have precise measurements, at least a 16-bit analog to digital converter. This just means the resolution of the whole voltage range can be divided into a number up to 16 bits basically. What you need to keep in mind though, most of the ADCs are not only measuring from 0 to, for example, 3 volts, they also most of the times measure from -3 to +3 volts. So you actually lose 1 bit. So you only have, basically I now have a 15-bit resolution. This is still totally fine and is in line what other data loggers can do. But for example, you could also use a very high precision one, but then we really would have to look out for if the dendrometer can even provide such a resolution, or if there's then a lot of noise. That doesn't help either. And we are already at a resolution of 0.8 micrometers, which is, it's okay. Yeah, you can work with that. So maybe you noticed, okay, I have the microcontroller and I have the ADC, and now I could attach here my dendrometer. But there's another chip down here. This one you don't have to. Drains, the voltage of the battery changes, and if you want to do measurements and calculations of the voltage of the battery and from the ADC, you need to know the exact voltage, and so I need some kind of reference that I can work with. So works with 2.048 volts, because this is the voltage reference that I choose. Why I choose 2.048 volts is relatively easy to say. The ADC has different ranges you need to set. I cannot say, okay, please work with 3.56 volts. I have to choose one of the predefined ones that are implemented in the ADC, and there's a range from minus 2.048 volts to plus 2.048 volts. That's the only reason why I choose this. These are pretty accurate, but actually I can measure the voltage with the ADC and then somehow know how far off I am. And this is the whole package. You need to calculate one resistor, so there's the right amount of current consumption that can be used over the reference voltage. But that's it. That's the whole idea on how to read a dendrometer with LoRaWAN. I tried before, this one was 3 volts reference, because before I thought, why not? And then I found out, oh, I can only set it to a specific range, and then, okay, I just bought the same chip, but with 2.048 volts. No. This can be gone. Yeah. So okay, yeah, I tested with this. It worked. Yeah.
Yeah, but you mentioned in Tampa
Yeah.
you had a problem with, before you said you can run a LoRa or whatever measuring system for years on one battery,
Yeah.
and then you admitted that at Tambopata
The battery probably drained.
it worked for 5 days.
It worked for 5 days. The problem was, as far as we know, because I didn't even found this out with this project. I have my I have a private project in the church in Xanten, which we visited yesterday, and I worked with Henrik there. I don't know if you met him at all, but yeah, I worked with Henrik on this project, and there we also had a sensor with the same CubeCell chip. And for some reason, we had some sensors that worked on one battery for, I think now 8 or 9 months, and they already sent over 700,000 data sets.
700,000
From one battery, and it's still not empty. So it's still ongoing. We want to reach the no, no, no. It's like one of the small ones, 3,600 milliamp hours. Yeah. But then we developed a new sensor that could also has another sensor included, and this was just gone after 2 weeks. And we wondered, hey, why is this? And then we measured actually the very precisely measured the power consumption, and then we noticed it's much higher than with the other modules. And what we found out with it seemed to be a new batch or something, that some of the floating pins, because if there's nothing connected to a pin, this could use power. And then we found a software way to define, okay, please block all of them and just don't use them, don't provide any power to them, and then this fixed the issue. So my guess is, because the same happened in Tambopata, that the battery just died. That's basically it.
This is important to note, right? In case, I think
Yeah.
several people who already have a lot of experiences with microcontrollers, and they are selling these things as low power, right? And the CPU core has the lowest power consumption ever, but you need the right connection, the right electronics, so the whole environment has to be low power designed. And you can do a lot of mistakes with that, right? You think you would have a low power design, you put the microcontroller to sleep, and the board still drains milliamps instead of microamps, right? And so this is a very difficult problem still, and this is really challenging. I'm glad that you made this experience to see how this is in the real world, and what you have to do is to avoid all these typical mistakes you're doing, and also to test, and best not in the rainforest, but maybe even in the garden, right?
I mean, therefore, so what came after this that I can now show you? I built my first PCB, the first PCB version, and it looked like this. I can zoom in a bit. So this was the first version I made. Because it was kind of in a hurry, I did this in 4 days. So from the breadboard to the PCB, and then I had to fly to Peru. So it was kind of in a hurry. But still, we managed to do something. And as you might see, this is the same module. They just changed the appearance a bit. And everything is basically on here that's needed. What I left away is, for example, a USB to serial converter, which is needed to program the board, because it's just not needed during measuring. I only need it once for programming, and that's it. Then I don't care for it anymore. But the rest of the components are basically the same as on the breadboard. So you can see this chip here, for example, is the analog to digital converter. This down here is the reference voltage, and there are just some, I think these are MOSFETs to turn off the power, for example, to the ADC, because during deep sleep, when I'm sleeping and not measuring anything, I don't need them to be turned on. So I save a lot of power. I had some issues. So for example, there was the one issue that the battery drained. This was a software problem. I also had problems with the antenna, the coil right here. We had some great experience before, but with this I couldn't really get them to work properly but this is also due, maybe you can now see it better. When you make an antenna, you have to look out for that there's no ground under it, because this will completely, how can I say it nicely, change everything basically. And when you see here, this lighter green has no copper under it at all, and this darker green is copper, basically. There's some copper under this. I don't even know what it is. It's a screen, a silk screen. And you see here the antenna is definitely over this. So that's what I guess was the problem with my bad connectivity. Meanwhile, I did a second version after I came back. You can see one other board right here. Kind of looks the same, but now I have much more room over here to have a bigger antenna here. So now there's no ground on it, no influence. Else there isn't really much that changed. I just changed up some stuff here that was needed for programming, which I then said, okay, I can also put it on another board. So I save on components. And I think there's no even a third version after this. So it's constantly improving basically. And yeah, we tested the new version. Unfortunately, I didn't brought the device to measure the power consumption of boards like this, but we have one from Nordic. That's how the company is called, and we can measure up to, or down to rather, to microamps. And with the new design, I can actually get down to 10 to 15 microamps during sleep, and around 2 to 3 milliamps on average over the measurement and sending period. And with this, we should get well over 2 years, hopefully, on one battery. And as you can see, the battery fits like in these clips, and you can just clip it in and that's it. So everything is then in the end confined in in one housing. And actually I choose this housing because it already is pre-manufactured with like a cable pass-through, so it came like this and I don't need to modify anything, drill holes or something. Unfortunately the antenna is still a bit of a problem, so I drilled a hole and put an antenna on it. Yeah. Yeah. Mm. Antenna, yeah. Yeah, the only problem is I need to choose a new housing then. But that's it. Because if you see, this really just fits in barely. Now there's in the battery, so it's still a bit lower. But if I close this, basically it's already at the maximum. And this isn't great. Yeah. Mm-hmm. 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 Yeah. Mm. I also thought about going with like an SMD antenna, so this would be just a patch, and I would have enough room for that. Basically, this would be version 4 that I want to make basically, but I still have to choose like one of the many. Meters. Right. Yeah. Yeah. I still need to find a way to put a matching circuit on it then, because right now we don't do any of the matching, because there's some matching in here as well, but with like a patch antenna we will definitely, or like a SMD antenna, we will definitely need it. Yeah. Yeah. The only thing we aren't sure about is, here's a UFL connector on the on this module, LoRaWAN module itself, and it's connected to one of the pins. So you can either do like soldering it here or put it or put a UFL antenna here. What we did for measuring, just to try out, what we did before was connecting our network analyzer to this UFL, which is then also connected to here. But what? Yeah, the UFL was just the network analyzer, just to find a way in. But I think what happened is this isn't working because there's some circuitry in here, and we should just connect without the module just to the pin, right?
Because kind of modules you can choose between the UFL or
Mm.
external.
Yeah.
So there is a bridge you have to solder or unsolder.
No, but with this actually not. Both are connected at the same time.
Then you must use or the antenna
Yeah.
or disconnect the antenna and put another analyzer. Only one.
Yeah. There's only one. We just connect the network. Yeah, the vectoral network analyzer to the UFL. So just as a pin to have a connection to the antenna pad. That's how we use it. But I think that's not the right way to do it. Yeah. This is like details.
But in fact, this is what causes the real problems in the field, right? That would
Yeah.
be a tight water tight case,
Yeah.
the antenna, and then you have these ants and the snakes and what other bad animals,
Yeah.
right?
You mean, so this is how one of the housings looks like that's already there. And you see they just eaten through it, and I think they use silicone, Eric? Was it silicone? Yeah. I will not use silicone, it's not worth it.
Ants entered the case and they built kind of nest there. Or
Something.
we also have this anaconda pattern here. What was it?
The small one? But this was on top of the tower.
At 40 meters height.
Yeah. Ask Eric, I don't know.
And Christoph is probably fighting with polar bears or so. He likes python. But in the anaconda distribution.
Yeah. Here you can see the dendrometer, and I was installing the new one. Yeah. Yeah, this is the journey we normally take when developing such sensors. They are not perfect yet, but we are working on them.
But everything is open source, of course.
Oh yeah.
We're willing to share, and we are pretty much beginners, I would say, but we are on the right way. So it's gonna be working in the end.
Hopefully. I mean, I can show that the Wi-Fi seems to work now for the last half an hour. So, so there are two dendrometers with LoRaWAN nodes right now out there. One of them has a smaller antenna, one of them has a bigger antenna. The one with the smaller one is not working as well, to be honest. But the bigger one actually worked for the last 1.5 weeks or so. What I'm now showing is the influx database. So we're using a time series databases, or at least I like to use them. Rolf uses normal databases for some reason.
All of that is open source.
Yeah, we most of the time only use open source software. So what I'm doing, maybe I can show like all of that. Ah, yeah, I still need to have /QI there. Because you want to kind of understand how everything after the sensor, after the gateway works. I will now show that to you. No, I want to switch.
So that is the LoRaWAN
Yeah.
network application server.
Right. So what we use here, because we are not on the edge really, we have most of the times a good internet connection here. We normally use the Things Network, which is a community-based network and application server, as Rolf already says. And what we can do here, we can open our gateways to the whole community. So with LoRaWAN, what you can do is make all sorts of different networks. You can use, you can make a private network, you can make public networks, but you can also do like hybrid ones and community-based. So the Things Network is solely community-based. And it's free of charge. There are some, as you can see maybe in the top, there are some fair use rules that you have to follow. So you cannot send every 20 seconds or something. That is not really in the favor of the community then. but else you can register your gateways here and so build up a whole network around the world just with infrastructure from the community. And that's the great thing. So we have some gateways here, as you can see. Most prominently are the top ones, the newest ones, which are connected. They are up on the tower.
When you connect these gateways, everyone
Yeah.
can use them, right? It's not exclusive usage, but as you register them, they are free to use. That's the idea.
So what we can see here is like the coverage, and TTN Mapper is also community project, and everyone can test the LoRaWAN or the Things network coverage with devices like, I think I have one of them here. Let me check. With devices like these. What this is basically, it's like a small package, I think made by Seed, M5, which basically has a screen, it has a small battery here in between, and the LoRa module, and it also has GPS. With this I can just walk around, and then the device tries to connect to the Things network, sends a message, and then looks what comes back. In the message to the Things network are also the GPS coordinates, and if the pack or the LoRaWAN packet sent was successful to a gateway, then it will be shown almost live. Normally there are a couple of hours of delay here on the map. So every one of these points is actually someone that tested this. So I probably am one of these here that goes up to Goch or Kleve, because that's my route I drive with my car, and I just laid it in front of my car and tested it. But what we can do here actually is also see how our gateways perform. So you see these, we are here. Can also show maybe on a satellite. You can already see the Fab Lab, the green Fab Lab here, and here's the tower. And actually if I click on that, I can see how this gateway performs, and actually can see all the I can see all the beams, so where it connected to. And you see this is kind of far away. So if I measure this with this tool roughly, this is already around 20 kilometers that we can that we cover with our gateways here. And the same goes for the other gateway. So we are providing the Things network connectivity for basically Camp Linford and the surroundings. This one was our best result we had so far, as you can see if it loads. Oh, there's actually a new one. One of these is new. And you see here's Düsseldorf, and this is even after that. So with LoRaWAN and our high position here, we get a range of 46 kilometers. This is should be taken with a grain of salt. It's probably line of sight. I think that area is a bit higher up. As well, so yeah, but in theory and in some practical tests you can get very good ranges.
With a free line of sight.
Yeah.
This is artificial. You don't have that in the real world, right? You are in cities with a lot of street canals, with buildings in between, trees, right?
Trees, yeah,
Like
trees.
Amazon forest, they have trees, and within the trees maybe a few hundred meters or so max, I would say.
Yeah.
But there are even some initiatives where they're trying to set up a kind of multi-hop network based on LoRa in forest.
Yeah, they use it for. I like how you can switch between German and German, but okay. They have these mesh gateways. These also use LoRa, and then they work solely from solar and then mesh under each other, and these are meant to be used in forests, for example. So you have one node on the edge, which has actually connection to the internet somehow, and then these can be scattered around the forest to build up a LoRa network inside without actually needing 4G connection down there. That's the whole idea.
So you have a multi-hop network which artificially, or with which you then extend the range.
Yeah, here you can see it.
It's really a good idea to have a really big tower.
Absolutely.
Because that's its line of sight.
Yeah.
Christoph loves big towers and Erik as well.
Yeah.
I don't have a connection here. Christoph, please set up the tower. Okay, how much? 30 meters, please.
Yeah.
I'll bring it.
I mean, actually, when we were in Tambopata, the Wi-Fi around the tower is okay, right? Yeah, the tower now has Wi-Fi as well. It's around like 20 meters around the tower. Good Wi-Fi connection. But yeah, so we have installed our gateway and connected it through the Things network. And here we can actually set up applications. Applications are just used to divide all the devices, so you don't want everything in one place, because as you can see, here is some test for the Andesflux. Here's our stuff for the LINEC, and we have our cow trackers, for example, and they are all divided. But let's look here. We just have, I think, 3 devices. This was for testing before. And you see one of them isn't working, but this one actually works. And what I can see here is like the device, the end device ID. I can just give it a name basically. I can see on which frequency it runs, because we're in Europe. We use 868 megahertz. And I can also see what Rolf mentioned before. I can see the device EUI, which is like a unique ID per device, so you can differentiate every device. And then the app key is basically a password. And that is everything needed. But now you think, okay, what we mentioned before, we're just sending bytes. And yeah, bytes are not that good to work with. So we somehow need to format the whole thing. And that's what payload formatters are for. So you can program in JavaScript actually. Mine is, I think, here. You can program in JavaScript how to get from bytes back to actual values, so that I can get, for example, okay, I just want the micrometers and I don't want 4 bytes or something like this. So actually I developed like a small protocol so that all the sensors are roughly the same. And this actually supports multiple sensors. For example, it also supports temperature and humidity sensors as well, and they are just all done the same. And for example, here's the ADC value, so I can read a 16-bit ADC value converted back to a float, which I did in my free private time. Not at the university, but we still use it. Yeah. And so the payload gets decoded after. Can I please? I want to see my end devices again. So the payload here gets decoded. You can see that here. Somewhere, yeah, here you see the actual stuff that gets decoded. So I divide my payloads into frames, so I know, okay, I have this temperature sensor, which is sensor number 1, and it shows 7.88 degrees. Then here I can see, okay, but there's also a humidity sensor. With it seems to me the humidity in the enclosure is quite high currently, which isn't the best thing, but fixable. And then you can see this ADC value, so sensor number 3, 2796. This is the actual value that the dendrometer gives out. And with this I can later work. And I can also get the battery value. That's basically it. And this is all coming from the bytes, and it's decoded by the payload formatters. What I can then do from TTN, I need to somehow send the stuff out, all my data. And for that, normally we use MQTT, but you see there are also other integrations possible. You can also do like normal HTTP requests. We use MQTT for the simplicity of it, and it works pretty well.
To make it clear, so the sensors
Yeah.
send the data in the end to the application in the LoRaWAN server, and that buffers the data only, I don't know how long or how many.
Not at all.
Not at all.
It shouldn't.
You have to get the data from the TTN server, and you can do this by a publisher-subscriber
Yeah.
mechanism, which is using the so-called MQTT protocol. It's a very, I would say, widely used protocol in IoT environments, and that allows you to basically serve the data, the decoded data, in an MQTT package, and then people with access can then subscribe to the data, and each subscriber gets a copy of it, which means that this is really nice, because you can share this information with your friends and say, okay, there is a sensor at Tambopata, if you want to use it, hook to the MQTT, and then you get the data.
store it locally on the databases.
And
And this is the idea of a publisher, subscriber, software pattern.
in theory, you can even control it over that. So the devices, the dendrometer, can also be controlled. So you can, for example, change the interval from basically sitting here. And this could also be done over MQTT if you have the rights to do so. Just as a side note. So there's also a way from here to the sensor and not only in one direction. So it's a bidirectional communication.
Oligo's question, right? Can you also use it as an actuator?
Oh yeah,
Which means there is also a way back.
yeah,
So not just upstream, but also downstream.
basically. And what we are using to then further investigate on the data and handle it a bit, put it into a database, we use Node-RED, which is an open source flow-based system. Yeah. So everything can be done with nodes, and you can also code in JavaScript, of course. So here we have a node, an MQTT node, which subscribes to the MQTT server or broker, as Rolf already explained. We then get a message then get this message, basically, that I just showed. What I then do, I filter all the devices and then see if I actually want to have the data in my database. And then I will save it afterwards into the influx database I was showing earlier. So this is really just for handling the data. I can do extra calculations in here and then put it into the database. That is everything that I do in Node-RED, but we can use it for other stuff as well.
You can show how to set up a new script or so, right? How would you add another MQTT connection here?
Oh, yeah. So you see everything is node-based. I can also do HTTP, for example, but with MQTT in, so I want incoming MQTT messages. I have to select the server, which I first need to set up, but I just select this one here. And then everything has topics. These topics are predefined from the Things network. And for example, this is v3 / and then plus means I want all the applications. Then I want the devices and all the devices. I don't care which device. I will take care of that later. And then I want all the uplinks. So everything that got sent from device to the server, basically. And this topic I can define here. Yeah. Yeah.
You can imagine then this receives packages, and then you can convert these packages and pass them to the next block, which does something else, right?
Yeah, right.
Even add some JavaScript blocks
Yeah.
if you like, but
And
usually you also have some standard blocks like pass the data to the database.
right.
And the nice thing here is that you can also here dispatch the data easily, right? You distribute it
Yeah.
in several ways, right? Whoever has this MQTT
Login, yeah.
login, right, can subscribe to the data and receive it, and then you can even define alarms and say, okay, when the temperature falls
Right,
below
yeah.
a certain threshold or so, send me an email. So that's really a low code.
Yeah.
We like it very much.
And because you have the ability to do HTTP stuff basically here, you can also send out HTTP requests. You can also talk to all sorts of APIs. So this is adaptable for other use cases as well. So for example, what I can show, I mentioned in my presentation that we can already do file syncing between the LiCore system and our server basically. And this is all done in Node-RED as well, which makes it very easy to understand as far as I can tell. So right now this isn't automated, but what this basically does, okay, I have a start, so a trigger. I want to trigger an automation. This could be done periodically. And then I want to set, okay, I want to look a specific directory on the LiCore system.
Which means you would connect here to the Tambo Pasha tower.
Right, right. So this is connected over the VPN already to the tower. So the server and the tower are always connected. Then I can just log into the LiCore system over SFTP. So SFTP is just a protocol to access the file system on a server or computer. So you see here, this is the local IP address of the LiCore system. And then I will just get all the files that are available in the directory. And what I then do is just enumerate over them and see, do I already have the file? If I don't have the file, it goes into here and basically downloads it. And I make a small queue out of it because I don't want to overload the whole connection. And then I will download all the files basically that are not in my file system already. That's the whole thing basically. And now I made yeah, I synchronize the folders in Node-RED already. And I could add more folders, for example, but right now, that's what I can set here. You can see this is on the Lycor system, I access the data raw, but I could also access other directories as well. So you see it's very flexible, and to be honest, some of the stuff here is not even implemented directly in Node-RED. It's contributed by the community. So the whole SFTP and loop stuff are modules you can install later on and are just there from the community, and it's been working pretty well for me so far. And that's basically it. So after here we get into the database. And I do already some calculations here.
And the next step is then maybe to use Grafana for a more sophisticated view, right?
Yeah.
You can show the weather station.
The weather station that isn't working currently, yeah, but I can show the LatiNet one.
Crash of the network.
Yeah, and something now is kind of broken with it. So we hope to fix it with the new. Yeah, but I have the Linux stuff. And this also, like the server is somehow overloaded currently. Or something is wrong with the Grafana, which is pretty old, and we need to update it. But I want to do this on the new server, not on the old one. Because we also need to set up a lot of stuff then. It doesn't load at all right now. There it is. That's what I mean. I don't know what happens. I restarted it, didn't work. But here I can show you the, yeah. So here you see there it was in the lab, we did some work on it. But I want to zoom in, which I can just do by this. Here it has a predefined range from 0 to 2.5 meters, but here actually Grafana decides on itself which is the best range it should show. And here you see the water is really changing slowly. And this is from... No, not really. Yeah. It's... Yeah. But in Grafana you can all sorts of a visualization basically.
So this is directly linked to the InfluxDB.
Yeah.
So after
Yeah.
a year or two, you're maybe just interested in the average temperature, whereas in the Grafana is an open source viewer or panel dashboard development tool, you can say, with which you can easily interact with the database, right? And what I really like here is, so we have usually this weather station where you see all the sensors on one glance.
Maybe I can
also
show.
the axes are synchronized. When you zoom in one of the axes and zoom in the time, then also the other
Maybe
automatically stay.
I can show. You can suffer, but I have. Grafana. And I can already say here, I think it was like this, I can now add an annotation. I want to do add annotation. Because yesterday we did some maintenance. So somehow. Save. But yeah, it's a very powerful tool, and I think this is also kind of fast if you think about Here we measure actually every 30 seconds right now. So it's a lot of. Yeah. Yeah, some of these are fairly new, and here we had a bug with negative temperatures, but we fixed it meanwhile. So yeah, it's been working good.
Okay, so if you like, we can. Is there anything to add from your side?
Basically, no.
So if you want, we can do some hands-on if you still have power to use this motor and play a little bit. Maybe. So
Introduction to IoT sensor and data processing. So actually, this is something we do with new students every 2 semesters. AMC.
we do this with schools now, right?
Yeah,
Frequently.
kind of. Yeah.
Yeah, I don't know. So Antonio is interested. Somebody else, also Daniel.
Yeah.
So that would suck up. Then let's go. Huh?
Yeah, I can get out the kids.
Thank you first of all.
So yeah, we can do a short break and then I will get all the stuff ready.